So here is something worth sitting with for a moment. Right now, wherever you are, there is a clock nearby, maybe on your phone, maybe on the wall. And that clock is dividing time into 60 seconds per minute and 60 minutes per hour. Not 50, not 100, 60. And if you have ever wondered why 60, the answer is that roughly 5,000 years ago, in a river valley in what is now Iraq, a civilization called the Babylonians decided that 60 was a really good number for counting. They liked it because you can divide 60 cleanly by 2, by 3, by 4, by 5, by 6, by 10, by 12, by 15, by 20, and by 30. And that decision, made by people who wrote on clay with sharpened reeds, still governs the way you read the time right now, tonight, in the dark. Or consider this: every single building you have ever walked into is standing because someone, somewhere, understood the relationship between the sides of a right-angled triangle. Every bridge you have ever crossed, every roof that has ever sheltered you, every satellite orbiting overhead, all of it depends on a rule about triangles that was being used by Babylonian surveyors 1,000 years before the man whose name we attach to it was even born. Or here is one more. Your phone, the one that might be resting on your nightstand right now, runs on a system of ones and zeros, binary, on and off, billions of times per second. And that system was anticipated, almost eerily, by Egyptian scribes more than 3,000 years ago, who figured out that you could multiply any two numbers together using nothing but the ability to double and add. They were playing with binary before anyone had a word for it. Mathematics is older than writing. It is older than cities. It is older than agriculture. Before human beings planted the first crop or built the first wall, someone, somewhere, was scratching marks onto a bone, keeping count of something, tracking the days or the seasons or the animals in a herd. And from that simple impulse, that urge to count and measure and find the pattern hiding inside the chaos, an entire universe of ideas has grown. Ideas so powerful that they literally hold the modern world together. And the strange thing, the thing that I keep coming back to, is that all of those ideas, every single one, from the mathematics that keeps planes in the air to the mathematics that encrypts your text messages, all of it grew out of 4 questions. 4 very simple questions that you already know how to ask, because you have been asking them your whole life without realizing it. The first question is one you ask every time you check your bank account, every time you split a bill, every time you glance at a price tag. How many? How much? Can I count it? Can I track it? Can I trust the numbers? You use numbers every single day, and they feel solid, reliable, obvious. But where did they come from? Who decided what a number is? And here is the unsettling part. When mathematicians followed that question as far as it could go, they discovered that the numbers you rely on are just one thin layer of a structure so vast and so strange that it contains different sizes of infinity. That some infinities are genuinely, provably larger than others. The man who proved this was called a corrupter of youth by his colleagues and spent the end of his life in a psychiatric clinic. All because he took the question "how many" seriously enough to follow it wherever it led. So the numbers on your phone screen tonight, the ones that feel so simple and harmless, those numbers have a wild side that almost nobody talks about. The second question: is one you answer every time you walk into a room and judge the distance to the door. Every time you parallel park. Every time you look at a map on your phone. What shape is it? How does the space around you actually work? You probably assume that space is flat and that geometry is settled, that the angles in a triangle always add up to 180 degrees, the way your teacher told you. But that is wrong. The actual space you live in, the physical space between you and the wall, is curved. Not metaphorically, literally, measurably curved, bent by the mass of the earth beneath you. Your GPS knows this. If it used the flat geometry you learned in school, it would drift by about 7 miles a day. The geometry of reality is not the geometry anyone expected. And the story of how we found out is one of the great intellectual adventures in human history. The third question is one you face every time something in your life is moving, growing, or falling apart.
What happens when things change? How do you measure something that will not hold still? Your heart rate changes. Your savings grow or shrink. The weather shifts. You live in a world of constant motion, and the entire mathematical framework for dealing with that, calculus, was invented by two men who despised each other, rested on an idea so logically shaky that one critic called it the ghost of a departed quantity, and yet somehow worked so well that it predicted the orbits of planets and built the modern world. It took 150 years before anyone could explain why it actually worked. The tool was built long before anyone understood the ground it stood on. Every time you check a weather forecast, every time a plane stays in the air, every time your phone streams a video, you are relying on mathematics whose foundations were not sorted out until generations after it was invented. And the fourth question is maybe the most dangerous one of all, and it is one you have probably asked yourself in some form. Can I be absolutely sure about anything? Is there anything in your life, anything at all, that you can know with perfect, unshakable certainty? Mathematics tried to answer yes. For thousands of years, mathematical proof was the gold standard of certainty, the one domain where a true statement stays true forever, where no new evidence can overturn it, where the conclusions are permanent. And then, in 1931, a quiet 25-year-old Austrian named Kurt Gödel proved that even mathematics has limits, that certainty itself has a ceiling, that in any mathematical system powerful enough to describe basic arithmetic, there will always be true statements that cannot be proved. The dream of perfect, complete knowledge is, and always will be, impossible. And he proved this with a proof. So if you have ever wondered whether there are things that are simply beyond the reach of human understanding, things that are true but that we can never, ever demonstrate, the answer is yes. And we know this for certain. These four questions, how many, what shape, what if it changes, and can I be sure? These are the threads that weave through the entire history of mathematics. And all four of them are woven into your daily life, right now, whether you notice them or not. Every theorem, every breakthrough, every bitter argument, every moment of sudden clarity across 4,000 years of human thought, all of it connects back to one or more of these questions. And what makes the story so extraordinary is how these threads keep tangling together, how a question about counting leads to a question about shapes, which leads to a question about change, which leads to a question about certainty, and then loops back around to counting again, but at a deeper level, a level that the original counters could never have imagined. So settle in, get comfortable. We are going to walk through the entire history of mathematics tonight, and we are going to take our time with it. We will start 20,000 years ago,
with a bone covered in scratches. And we will end up, eventually, with questions so deep that the smartest people alive cannot answer them. Along the way, we will meet a man who was murdered for discovering a number that should not exist, a woman who was torn apart by a mob for teaching mathematics in the wrong city at the wrong time, a boy who wrote down the foundations of an entire branch of mathematics the night before he was killed in a duel at the age of 20, and a reclusive genius who solved one of the greatest problems in the history of human thought and then turned down $1 million because he did not want the attention. All of it, every piece, connects to those 4 questions. And all of it, every piece, connects to you, right now, tonight. Because the mathematics that grew from those questions is not locked up in textbooks. It is running your world. It is in the signal carrying my voice to your ears. It is in the algorithm that chose to show you this. It is in the GPS satellites that know where you are on the surface of the Earth to within a few feet. You are swimming in mathematics. You always have been. You just might not have known how deep the water goes. Let's find out. Let's start with the oldest question. How many?
Before we get into civilization, before we get into Egypt or Babylon or Greece, let's go back further, much further. About 20,000 years ago, maybe more, someone living near the headwaters of the Nile, in what is now the Democratic Republic of the Congo, took the leg bone of a baboon and began carving notches into it. Deliberate notches, grouped in patterns. One column has groups of 11, 13, 17, and 19. Another column seems to show a doubling sequence. This object is called the Ishango bone, and it is one of the oldest mathematical artifacts we have ever found. Now, we do not know what this person was counting. Maybe it was days. Maybe it was lunar cycles. Maybe it was something else entirely that we will never be able to guess. Researchers have argued about it for decades. Some think the groupings suggest an awareness of prime numbers. Others think that is reading too much into scratches on a bone. And honestly, we may never know for sure. But here is what we do know. 20,000 years ago, a human being was organizing quantity. They were not just reacting to the world, they were structuring it. They were grouping things and recording the groups, which means they were already doing something that goes beyond what any animal does. Because animals can sense quantity. A crow can tell the difference between 2 and 3. A lioness can look across a river and judge whether her group outnumbers the rival pride. But that sense is fuzzy and approximate. It falls apart once the numbers get bigger than about 4 or 5. What the person who carved the Ishango bone was doing was different. They were externalizing their count. They were taking the idea of a quantity out of their head and putting it into the world, locking it into a physical object that could be checked and referenced later.
And that seemingly simple move, the move from sensing quantity to recording quantity, is arguably the most important intellectual step our species has ever taken. Because once you can record a count, you can compare counts. You can track change over time. You can plan ahead. You can manage resources. You can build a civilization. And that is exactly what happened, slowly, over thousands of years. People went from scratching bones to arranging pebbles to making marks on clay. The Latin word for pebble, by the way, is calculus. Every time someone uses that word, they are reaching back to a time when mathematics meant lining up little stones on the ground. Now let's move forward a few thousand years and arrive somewhere warmer. The Nile Valley, around 6,000 years ago. People are settling along the river, farming the rich land that the annual floods leave behind. And very quickly, they run into a set of problems that demand counting and measuring on a much larger scale than any hunter-gatherer ever needed. The Nile floods every year. When it recedes, it leaves behind fertile soil, but it also washes away every boundary marker. Every single year, the Egyptians had to figure out who owned which piece of land all over again. They had to resurvey everything, remeasure every plot, recalculate every area. And they had to do this fairly, because if a farmer's field got smaller after a flood, he expected to pay less tax, and if it got bigger, the pharaoh expected more. This was not abstract mathematics. This was the tax system. Getting it wrong meant angry farmers or an underfunded government, and neither of those is a situation anyone wants. So the Egyptians got extremely good at practical arithmetic. They developed a number system based on 10, which makes sense, 10 fingers. And they used hieroglyphs to write their numbers. A single stroke for 1. A symbol shaped like a heel bone for 10. A coil of rope for 100. A lotus flower for 1,000. A pointing finger for 10,000. A tadpole for 100,000. And an astonished-looking man with his arms raised for 1 million. These symbols are beautiful, but the Egyptian number system had a deep limitation. There was no place value. In our system, the symbol 2 can mean 2, or 20, or 200, depending on where it sits in the number. The digit's position tells you its value. The Egyptians did not have this. Each symbol always meant the same thing, no matter where you put it. If you wanted to write 999, you needed 9 lotus flowers, 9 rope coils, and 9 strokes. 27 separate symbols for one number. It is like writing in Roman numerals. It works, but it is clunky. And it makes arithmetic much harder than it needs to be. Despite this limitation, the Egyptians were remarkable problem solvers.
We know this because of a document that has survived almost 4,000 years, a scroll of papyrus about 13 feet long and about a foot tall, written by a scribe named Ahmes around 1650 BC. Ahmes noted that he was copying from an even older document, so the mathematics in it may go back another 200 years or more. We call it the Rind Papyrus, after the Scottish collector who bought it in the 19th century. The Rind Papyrus is essentially a mathematics textbook. 84 problems with solutions, covering arithmetic, fractions, geometry, and basic algebra. And some of the problems are wonderfully practical. One asks, how to divide 9 loaves of bread equally among 10 people? Which sounds simple, but the Egyptians had a particular constraint. They worked almost exclusively with unit fractions, fractions where the numerator is 1. So instead of saying each person gets 9/10 of a loaf, they would express the answer as 1/2 plus 1/3 plus 1/15. Each person gets those 3 pieces, and if you add them up, you get exactly 9/10. This seems cumbersome to us, but the Egyptians had elaborate tables for decomposing any fraction into a sum of unit fractions, and they could work with surprising speed and accuracy using this system. And there is something conceptually interesting about it. When you restrict yourself to unit fractions, you are forced to think about how quantities break apart into pieces in a very concrete, almost physical way. You are not manipulating abstract symbols. You are thinking about actual portions. But here is where Egyptian arithmetic gets genuinely clever. Their method of multiplication is beautiful, and it anticipates something that would not become important for another 3,000 years. Say you want to multiply 13 by 11.
The Egyptian scribe would make two columns. In the first column, you start with 1 and keep doubling. 1, 2, 4, 8. In the second column, you start with 13 and keep doubling. 13, 26, 52, 104. Now you look at the first column and find the numbers that add up to 11, which is 8 plus 2 plus 1. Then you go to the second column and add the corresponding values. 104 plus 26 plus 13 equals 143. And that is 13 times 11. What the scribe has done, without knowing it, is decompose 11 into its binary representation. 11 in binary is 1011, which is 8 plus 2 plus 1. The Egyptians were using the principle of binary arithmetic, the same principle that runs every computer on the planet, more than 3,500 years before Leibniz would formalize binary notation, and more than 3,500 years before binary would become the language of the digital age. Now let's shift east to Mesopotamia, because while the Egyptians were developing their mathematics along the Nile, something equally remarkable, and in some ways more sophisticated, was happening between the Tigris and the Euphrates, in the land we now call Iraq. The Babylonians built their civilization on clay. Literally. They wrote on clay tablets with wedge-shaped reeds, pressing marks into the soft surface before it dried. This writing system is called cuneiform, and thousands of these tablets have survived, buried in the dry soil for nearly 4,000 years. And when modern scholars deciphered them, they found something that surprised everyone.
The Babylonians were using a number system based on 60. Now, 60 seems like an odd choice. We are so used to base 10 that anything else feels unnatural. But think about why the Babylonians might have liked 60. 60 is extraordinarily divisible. You can divide it evenly by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. That is 12 factors compared to only 4 factors for 10. And when you are running an empire, when you are dividing grain among workers and splitting land among heirs and calculating taxes, having a base that divides cleanly by so many numbers makes life dramatically easier. Fractions in base 60 tend to come out as neat, finite values rather than messy, repeating ones. There is a theory about how they arrived at 60. You have 12 knuckle segments on the 4 fingers of one hand, not counting the thumb. If you use your thumb as a pointer and count those 12 segments, then use the 5 fingers of your other hand to count how many groups of 12 you have gone through. You get 5 times 12, which is 60. It is a speculative theory, but it is a lovely one. The idea that the human body itself suggested a number system that would prove almost magically useful. And we are still using base 60 today. Every time you say that an hour has 60 minutes or a minute has 60 seconds, you are using Babylonian mathematics. Every time you note that a circle has 360 degrees, you are dividing the sky the way Babylonian astronomers did, because 360 is 6 times 60, and the Babylonians noticed that the sun moves roughly 1 degree across the sky each day, and there are roughly 360 days in a year. The fit was not perfect, but it was close enough, and the number was so wonderfully divisible that it stuck.
For 4,000 years, it has stuck. But the most important feature of the Babylonian system was something the Egyptian system lacked entirely: place value. In the Babylonian system, the position of a symbol determined its magnitude. A wedge mark in one position meant 1. The same wedge mark, one position to the left, meant 60. Another position to the left meant 3,600. This is the same principle as our modern decimal system, where position determines whether a digit means ones, tens, hundreds, or thousands. The Babylonians simply used 60 as their base instead of 10. And this matters enormously, because place value is what makes arithmetic scalable. With place value, you can represent any number, no matter how large, using a small set of symbols. Without it, you need more and more symbols as numbers get bigger, and computation becomes increasingly unwieldy. The Babylonians could do arithmetic efficiently with very large numbers, which they needed to because they were obsessed with the night sky. The Babylonians tracked the movements of the moon and the planets with extraordinary care, recording their observations month by month, year by year, for centuries. By around 800 BC, they had complete lists of lunar eclipses. They could predict when the next eclipse would occur. And all of this astronomical calculation required working with very large numbers, which their base 60 positional system handled beautifully. But there was a problem. In the early days, when a Babylonian scribe wanted to write, say, 3601, which in base 60 is 1 times 3600, 0 times 60, and 1, they had no way to indicate the empty middle position. They would just leave a blank space, and the reader would have to figure out from context whether the gap was meaningful or just sloppy handwriting. Imagine trying to distinguish between 61 and 3601 when the only difference is the width of a gap between two marks on a clay tablet. Eventually, the Babylonians solved this by introducing a placeholder symbol, two small wedge marks placed at an angle. This symbol did not represent a number. It represented the absence of a number. It said, "Nothing goes here. Skip this position." And this is the first appearance of anything resembling 0 in the history of mathematics. But it was only a placeholder. The Babylonians did not think of 0 as a number in its own right. They did not do arithmetic with it. They did not add 0 to things or multiply things by 0. It was a punctuation mark, not a quantity. The journey from 0 as a placeholder to 0 as a full-fledged number would take another 2,000 years and would happen on the other side of the world, in India. But we will get there. The Babylonians were not just counting and tracking stars, they were solving problems that look remarkably like modern algebra. And they were doing it nearly 4,000 years ago. Many of the surviving clay tablets are school exercises. They were written by students learning to be scribes, the professional record keepers of Babylonian society. Scribe schools existed from around 2500 BC, and the training was rigorous. Students copied problems, solved them, and had their work checked. And the problems they solved were not trivial. Here is a typical example, translated into modern terms. You have a rectangular field. You know that one side is 6 units longer than the other. You know the total area is 55 square units. How long is the shorter side? In modern notation, you would set this up as a quadratic equation and solve it with the quadratic formula. The Babylonians did not have algebraic notation. They had no symbols for unknowns, no equal sign, no formulas written on a chalkboard. But they had a method. They would describe the steps in words, like a recipe. Take the coefficient, halve it, square the half, add the area, take the square root, subtract the half. Step by step, they would walk you through the solution. And the method works. It is in fact equivalent to the quadratic formula, just expressed verbally instead of symbolically. The Babylonians were solving quadratic equations more than 1,000 years before the Greeks. And they were doing it with a sophistication that suggests deep understanding, not just rote memorization. They also created something called Plimpton 322.
a small clay tablet about the size of your hand, covered in cuneiform numbers arranged in rows and columns. When mathematicians decoded it in the 20th century, they realized it contained a systematic list of Pythagorean triples, sets of 3 whole numbers where the square of one equals the sum of the squares of the other two: 3, 4, 5, 5, 12, 13, 8, 15, 17. 15 different triples, all with whole number sides, all satisfying the relationship that we call the Pythagorean theorem. And here is the thing that makes this remarkable. This tablet was created around 1800 BC. Pythagoras, the Greek mathematician whose name we attach to this theorem, was born around 570 BC. The Babylonians knew about the relationship between the sides of right triangles more than 1,000 years before Pythagoras was born. They were using it, recording it, teaching it in their schools. Now, whether the Babylonians understood why the relationship works, whether they had anything like a proof, that is a different question, and a controversial one. Some historians think Plimpton 322 represents a deep theoretical understanding. Others think it is simply a teacher generating nice numbers for homework problems. The debate continues.
But what is clear is that the Babylonians had a working knowledge of this relationship, and they used it extensively. On another tablet, a school exercise nearly 4,000 years old, a student drew a square and its diagonal. Along the diagonal, the student wrote a number. Translated into our decimal system, that number is 1.41421356, the square root of 2, accurate to 6 decimal places. Think about what that means. The student knew that if you have a square with sides of length 1, the diagonal has a length that cannot be expressed as a whole number or a simple fraction. The number goes on and on after the decimal point, never settling into a repeating pattern. We call such a number irrational. The Babylonians did not have that word, but they could calculate the value to stunning precision, which tells you something about their arithmetic ability. And it tells you something else, too. It tells you that the question of how many is deeper than it first appears. Because the moment you start measuring diagonals and circumferences, you discover numbers that do not fit neatly into the counting system you started with. Numbers that are not whole, not fractional, not expressible as one number divided by another. Numbers that sit in the gaps between the numbers you already know. The question of how many leads inevitably to the question of what kinds of numbers exist. And that question, followed to its end, leads to places that are genuinely unsettling. But we are getting ahead of ourselves. Let's stay with the practical, the tangible for a while longer, because the story of counting and numbers does not belong only to Babylon and Egypt. It was happening independently in other parts of the world, and each civilization brought its own innovations. In China, by around 1500 BC during the Shang dynasty, people were using a sophisticated counting system based on bamboo rods arranged in patterns. This system was positional, meaning the location of each rod determined its value, and it used base 10. The Chinese had a decimal place value system more than 1,000 years before Europe adopted one. They used counting boards, flat surfaces where rods could be arranged and rearranged to perform calculations. And with these boards, they could do arithmetic with remarkable speed and efficiency. By around 200 BC, the Chinese had compiled a mathematical text called the 9 Chapters on the Mathematical Art. It is their equivalent of Euclid's Elements, though it is organized very differently. Where Euclid built an abstract logical edifice from axioms and proofs, the 9 chapters presents practical problems with step-by-step algorithmic solutions.
How do you calculate the area of a field? How do you divide grain proportionally among workers? How do you solve a system of linear equations? And that last one is worth pausing on. The 9 chapters includes a method for solving systems of linear equations that is, step by step, identical to what we now call Gaussian elimination, the standard method taught in every linear algebra course in the world. But this was around the 1st century BC. Gauss was born in 1777. The Chinese had the method roughly 2,000 years earlier. They were also among the first to work with negative numbers. In their counting rod system, rods of one color represented positive quantities, and rods of another color represented negative ones. They knew that a negative number plus a positive number could give you a positive, a negative, or 0. They understood the rules for multiplying negatives.
This was around the 1st century AD, and it would be many centuries before European mathematicians would accept negative numbers as legitimate. Meanwhile, in India, something extraordinary was happening. Indian mathematicians were developing the tools and ideas that would eventually reshape the entire world's approach to numbers. The Indian contribution to mathematics is immense, and it is centered on a single, deceptively simple invention. A symbol for nothing. The number 0. Now, we already talked about how the Babylonians used a placeholder for empty positions, and other cultures had similar notions. But it was in India, gradually over several centuries, that 0 transformed from a placeholder into a number, a quantity you could add, subtract, multiply, and reason about just like any other number.
By around 628 AD, a mathematician named Brahmagupta, working at the Astronomical Observatory in Ujjain, in what is now Rajasthan, wrote a text called the Brahmasfuta Siddhanta, and in it he laid out explicit rules for calculating with 0. 1 plus 0 equals 1. 1 minus 0 equals 1. 1 times 0 equals 0. He even tried to tackle division by 0, saying that 1 divided by 0 equals 0, which we now know is not correct. Division by 0 is undefined, but the fact that he was thinking about it at all shows how seriously he took 0 as a mathematical object. Brahmagupta also did something else that was revolutionary. He worked with negative numbers and gave them a coherent, systematic treatment. He called positive numbers fortunes and negative numbers debts, and he figured out all the rules. A fortune plus a fortune is a fortune. A debt plus a debt is a bigger debt. A fortune minus a bigger fortune is a debt. A debt times a debt is a fortune. This last rule, that a negative times a negative gives a positive, is something students still struggle with today, and Brahmagupta nailed it in the 7th century. Indian mathematicians also developed the decimal place value number system that we use today, the system where you have 10 symbols, 0 through 9, and the position of each digit determines its value. This system is so natural to us now that it is hard to imagine a world without it, but it was a genuine invention and it took a long time to spread. The way it spread is a story in itself. Indian mathematical ideas traveled west through trade routes to the Islamic world. In the early 9th century, a scholar named Muhammad ibn Musa al-Khwarizmi, working in Baghdad at the legendary House of Wisdom, wrote a treatise explaining the Indian number system to Arabic-speaking readers.
He also wrote a book on solving equations, whose Arabic title, Al-Kitab al-Mukhtasar fi Hisab al-Jabr wal-Mukabala, gave the world a word. Al-Jabr became algebra. And Al-Khwarizmi's own name, Latinized as algorithmus, gave us the word algorithm. Two of the most important words in modern technology, algebra and algorithm. Both trace back to a single 9th century scholar working in Baghdad. Every time a computer follows an algorithm, every time a student solves an algebraic equation, they are participating in a tradition that Al-Khwarizmi systematized 1200 years ago. His books were later translated into Latin, and through those translations, the Indian Arabic number system reached Europe. The numbers we call Arabic numerals in the West originated in India, traveled through Baghdad, and arrived in Europe through these Latin translations. Al-Khwarizmi's book was not purely abstract. He wrote it because people needed practical mathematics for dividing inheritances according to Islamic law, for calculating land areas, for resolving commercial disputes. The algebra was a tool for justice, a way of making sure that divisions were fair and calculations were correct. This deeply practical motivation is something that connects Al-Khwarizmi to the Babylonian scribes who came before him and to the software engineers who come after him. Mathematics as a tool for getting things right, for making the world a little more orderly, a little more fair. The person who did the most to introduce these numbers to Europe was an Italian named Leonardo of Pisa, better known as Fibonacci. Fibonacci grew up in North Africa, where his father was a trade official, and he learned the Indian Arabic number system from the merchants he encountered. In 1202, he published a book called Liber Abaci, the Book of Calculation, which demonstrated the superiority of the new system over Roman numerals for commercial arithmetic. And it was superior, overwhelmingly so. Try multiplying 1999 by 47 in Roman numerals. It is a nightmare. In the Indian Arabic system, you just multiply 1999 by 47 using the standard algorithm you learned in grade school. The position of each digit tells you what it represents, and the rules of arithmetic work smoothly and efficiently. Fibonacci showed this to European merchants, and slowly, over the next few centuries, the old Roman numerals gave way to the system we use today. But the story of numbers in India goes deeper than zero and negatives. A few centuries after Brahmagupta, another Indian mathematician named Bhaskara II, working at the same observatory in Ujjain around 1150 AD, pushed the boundaries further. Bhaskara wrote a text called the Lilavati, named, according to legend, after his daughter. The legend says that Bhaskara had calculated an auspicious moment for his daughter's wedding, and to time it precisely, he placed a cup with a small hole in it in a vessel of water. The cup was supposed to sink at the exact right moment, signaling that the ceremony should begin. But Lilavati, curious, leaned over to watch, and a pearl from her headdress fell into the cup, blocking the hole. The cup never sank. The auspicious moment passed. The wedding could not take place. Whether the story is true or not, Bhaskara named his mathematical treatise after her, and the Lilavati is a remarkable text. It covers arithmetic, algebra, geometry, and combinatorics, all presented in elegant Sanskrit verse. Bhaskara explored what happens when you divide by zero and arrived at the idea that the result is infinite, which is closer to the modern understanding than Brahmagupta's attempt. He also worked extensively with what we now call Pell's equation, a type of problem about whole number solutions that would not be matched in Europe for centuries. Indian mathematicians also made breakthroughs in understanding infinite series that anticipate calculus by hundreds of years. In the 14th and 15th centuries, the Kerala School of Astronomy and Mathematics, working in what is now the southwestern coast of India, discovered infinite series expansions for trigonometric functions like sine, cosine, and arctangent. Madhava of Sangamagrama, the founder of this school, is sometimes credited with developing the power series for these functions around 1350 to 1425, roughly 250 years before Isaac Newton and Gottfried Leibniz would derive similar results in Europe. Madhava and his successors could compute pi to extraordinary precision using these infinite series. One formula attributed to Madhava gives pi as 4 times the quantity 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9, and so on, alternating forever. This series converges very slowly, so it is not practical for computation by itself. But the Kerala mathematicians developed sophisticated acceleration techniques to make it converge faster, and they understood the basic idea of convergence, the notion that adding more and more terms gets you closer and closer to a definite value. The question of how much credit the Kerala school deserves in the history of calculus is genuinely debated. Some historians argue that Madhava and his followers essentially invented the core ideas of infinite series and should be recognized as co-founders of calculus alongside Newton and Leibniz. Others argue that the Kerala mathematicians, while brilliant, did not develop the systematic methods and the conceptual framework that make calculus a unified subject. The truth probably lies somewhere in between, and the debate itself is a useful reminder that mathematical ideas do not emerge in a vacuum. They arise in different places, in different forms, driven by different motivations. And the question of who gets credit is often more about the politics of history than about the mathematics itself. Let me also mention one more number system that deserves attention, because it illustrates just how diverse human approaches to counting have been. In Mesoamerica, the Maya developed a vigesimal number system, base 20, possibly because people in warm climates tend to go barefoot and can count on both fingers and toes. The Maya had a symbol for 0, independently of the Indian development, which makes them one of only a handful of civilizations to invent 0 independently. Their number system was positional, like the Babylonian and Indian systems, and they used it for astronomical calculations of extraordinary precision, tracking the cycles of Venus and the Moon over periods of centuries. The diversity of these number systems tells you something important. Different cultures in different parts of the world, facing different practical challenges, all converged on certain mathematical ideas: place value, positional notation, the need for a symbol for nothing, while diverging on others: base 10 versus base 60 versus base 20. The underlying mathematical truths are universal, but the paths humans take to discover them are wonderfully varied. So by the late Middle Ages, the question of how many had been answered in ways that the earliest counters could never have imagined. Humans had gone from scratching tally marks on bones to possessing a number system of extraordinary power. A system with place value, with 0, with negative numbers, with efficient algorithms for arithmetic. The toolkit was essentially complete for everyday counting and calculation. But the question of how many was not finished, because mathematicians kept pushing, kept asking, kept probing the edges of what numbers could do. And the deeper they pushed, the stranger things got. Remember that Babylonian student who wrote the square root of 2 on a clay tablet? That number, the diagonal of a unit square, is irrational. It cannot be expressed as a ratio of 2 whole numbers. And the discovery of irrational numbers was, according to ancient accounts, one of the most traumatic events in the early history of mathematics. The story goes like this. In the 6th century BC, a man named Pythagoras founded a secretive community in Croton, a Greek colony in southern Italy. The Pythagoreans were part mathematical school, part philosophical cult, part religious brotherhood. They had strict rules about diet, behavior, and secrecy. They believed that numbers were the fundamental substance of reality, that everything in the universe could be expressed as ratios of whole numbers. Music could. If you take a string and halve its length, the note goes up an octave. If you take 2/3 of its length, you get a perfect fifth. Beautiful, clean ratios. The Pythagoreans believed the entire cosmos worked this way. Harmony, order, whole number ratios all the way down. And then someone, tradition says it was a man named Hippasus, considered the simplest possible right triangle, one where both short sides have length 1. By the Pythagorean theorem, the hypotenuse must have a length whose square is 2. So the hypotenuse is the square root of 2. And Hippasus proved, using rigorous logical reasoning, that this number cannot be expressed as a fraction. No ratio of whole numbers, no matter how large, will ever exactly equal the square root of 2. The proof is elegant enough to describe. You assume the square root of 2 can be written as a fraction in lowest terms, say p over q. You square both sides and get 2 equals p squared over q squared, which means p squared is even, which means p is even. So p is 2 times some number k. Substitute that back in and simplify, and you find that q squared is even 2, which means q is even. But you said p over q was in lowest terms, meaning p and q share no common factors. You have a contradiction. The assumption must be false. The square root of 2 simply is not a fraction. According to legend, the Pythagoreans were so disturbed by this discovery that they tried to suppress it. Some versions of the story say Hippasus revealed the secret to outsiders and was drowned at sea as punishment. Whether any of that actually happened, we will never know. But the legend tells you something about how shattering the discovery felt. The Pythagoreans' entire worldview, their belief that whole numbers and their ratios were the fabric of reality, had a hole in it that could not be patched. There were numbers that were not ratios. The universe was wilder than they thought. This discovery forced Greek mathematics in a particular direction. If numbers themselves could be treacherous, if they could harbor these strange, irrational values, then geometry felt safer. You could draw a line segment of length square root of 2. It was just the diagonal of a unit square. You could see it, construct it, reason about it. You just could not write it as a fraction. For the next 2,000 years, geometry would dominate mathematical thinking, partly because of this unease about what numbers really were. Fast forward about 2,200 years. The question of how many had by then expanded to include not just whole numbers and fractions and irrationals, but also negative numbers and zero, and even complex numbers, numbers involving the square root of -1, which mathematicians had grudgingly introduced to solve cubic equations in the 16th century. The number line had been populated with an astonishing variety of mathematical creatures, but nobody had seriously tried to count the numbers themselves. Nobody had asked, how many numbers are there? The answer seems obvious, infinitely many. But in the 1870s, a German mathematician named Georg Cantor asked a question that nobody had thought to ask before. Are all infinities the same size? And the answer he found changed mathematics forever. Cantor's starting point was brilliantly simple. He asked, when can you say that two collections of things have the same number of elements? And his answer was, when you can pair them up perfectly, 1 to 1, with nothing left over on either side. If I have a collection of hats and a collection of heads, and every hat goes on exactly one head,
and every head gets exactly one hat, then I know there are the same number of hats as heads, even without counting either collection. Now apply this to infinite collections. The counting numbers go 1, 2, 3, 4, and on forever. The even numbers go 2, 4, 6, 8, and on forever. Your intuition says there should be fewer even numbers, because you are skipping every other one. But Quantara showed you can pair them up perfectly. 1 goes with 2, 2 goes with 4, 3 goes with 6, 4 goes with 8. Every counting number matches exactly one even number, and every even number matches exactly one counting number. No leftovers. In a precise mathematical sense, there are exactly as many even numbers as counting numbers. They are the same size of infinity.
Quantara called this size Aleph null.
This is already strange, but it gets much stranger. Because Quantara went on to prove that the real numbers, all the points on the number line, including all those irrational numbers with their infinite, non-repeating decimal expansions, cannot be paired up with the counting numbers. There are, in a precise and provable sense, more real numbers than counting numbers. The infinity of the reals is strictly larger than the infinity of the whole numbers. His proof, published in 1891, is called the diagonal argument, and it is one of the most beautiful proofs in all of mathematics. Suppose someone claims to have made a complete list of all real numbers between 0 and 1, written out as infinite decimals. Quantara says, I will build a number that is not on your list. For the first digit, I look at the first digit of the first number and choose something different. For the second digit, I look at the second digit of the second number and choose something different. I go down the diagonal. The number I build differs from the first number in the first position, from the second in the second position, from every number on the list in at least one position. So my number is not on the list. And I can do this no matter what list you give me. Therefore, no list can contain all the real numbers. The reals are uncountable. They represent a fundamentally larger infinity. And Quantara did not stop there. He showed that from any infinite set, you can build a strictly larger one by taking the set of all its subsets. So there is not just one bigger infinity. There is an endless hierarchy of infinities, each one incomprehensibly larger than the last. The reaction from the mathematical establishment was vicious. Leopold Kronecker, one of the most powerful mathematicians in Berlin, called Quantara a corrupter of youth. Henri Poincaré called set theory a disease from which mathematics would eventually recover. The resistance was not just intellectual, it was personal. Quantara suffered repeated bouts of severe depression throughout his life and spent time in sanatoriums. He died in 1918, largely impoverished. But Quantara was right, and the mathematics community came to recognize it, even during his lifetime. David Hilbert, who would become arguably the most influential mathematician of the early 20th century, declared that no one would expel mathematicians from the paradise Quantara had created. Set theory, Quantara's creation, became the foundation of modern mathematics. Virtually every branch of mathematics today is built on set theoretic foundations. When mathematicians define numbers, functions, spaces, or structures, they define them in terms of sets. The question of how many, pushed to its absolute limit, had revealed that infinity itself has structure, that there are layers and layers of it stretching upward without end. Let me pause here and do something that connects all of this back to the physical world. Because the numbers we have been talking about
are not just abstract curiosities. They are woven into the fabric of reality in ways that are genuinely startling. Consider pi. We mentioned that the Egyptians approximated it around 1650 BC. Archimedes pinned it down more precisely around 250 BC. But pi is not just a property of circles. It shows up in places that have absolutely nothing to do with circles. If you drop a needle onto a floor with parallel lines drawn on it, the probability that the needle will cross a line involves pi.
If you add up the squares of the reciprocals of all the whole numbers, 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, and so on forever, the answer is pi squared over 6. Euler proved this in 1734, and the result shocked the mathematical world because nobody could explain why a series about whole numbers would involve pi, a number born from circles. Pi appears in the normal distribution, the bell curve that governs everything from human heights to measurement errors. It appears in the equations of general relativity, which describe the curvature of space-time. It appears in quantum mechanics. It appears in the formula for the energy levels of a hydrogen atom. Wherever you find oscillation, rotation, waves, or periodicity, pi is lurking nearby. A number that started as the ratio of a circle's circumference to its diameter has infiltrated virtually every branch of physics and mathematics. Why? Nobody fully knows.
And pi is just one example. The number e, approximately 2.71828, originally arose from the study of compound interest, from asking how much money you would have if interest were compounded not yearly, not monthly, not daily, but continuously, at every instant. It turns out to be the base of the natural logarithm, and it governs growth and decay in nature. Populations grow exponentially. Radioactive substances decay exponentially. The voltage across a capacitor in an electrical circuit changes exponentially. The temperature of a cooling object approaches room temperature exponentially. Everywhere you find continuous growth or decay, there is E. The number I, the square root of -1, was introduced as a mathematical fiction to solve cubic equations in the 16th century. Cardano and his contemporaries called it a truly sophisticated number and treated it as a necessary evil, a convenient fiction that appeared in the middle of calculations but had to cancel out by the end. It took centuries before mathematicians accepted complex numbers as legitimate mathematical objects. And then, in the 20th century, physicists discovered that quantum mechanics, the most fundamental and successful theory of physics, cannot be formulated without complex numbers. The wave function, which describes the state of a quantum system, is intrinsically complex valued. The imaginary unit I, which was invented as a mathematical convenience to make algebra work, turned out to be essential for describing physical reality at the deepest level. The question of how many did not stay in the realm of pure abstraction. Every expansion of the number system, from whole numbers to fractions to irrationals to negatives to complex numbers, eventually proved indispensable for understanding the physical world. The numbers were not just human inventions. They were, in some sense, waiting to be discovered, because the universe was already using them. And the question is not finished. It never is. Right now, tonight, there are unsolved problems about numbers that the best mathematicians alive cannot crack. The Riemann hypothesis, which concerns the distribution of prime numbers and has been open since 1859, carries a $1 million prize. The Goldbach conjecture, which says that every even number bigger than 2 is the sum of 2 primes, has been verified for every even number up to 4 quintillion, but no one can prove it must always be true.
The Collatz conjecture, which involves a game so simple you could play it with a child, has resisted every attempt at proof despite its apparent simplicity. The question of how many started with scratches on a bone. It led to place value notation, to zero, to negative numbers, to irrationals, to complex numbers, to the transfinite hierarchies of Georg Cantor. 20,000 years of asking, and we are nowhere close to done. But counting and measuring are not the only things human beings needed to do, because the world is not just about quantities, it is about shapes. And shapes turned out to have secrets of their own, secrets that would take more than 2,000 years to uncover, and that would eventually reveal something shocking about the nature of space itself. That is where we are going next. The second question is about shape, and it begins, like so much of early mathematics, with mud. When the Nile flooded each year, it did not just deposit rich black soil on the farmland, it erased all the boundary lines. Every fence post, every marker stone, everything that told you where your field ended and your neighbor's began. Gone. And when the water receded, the pharaoh's surveyors had to go out and redraw every property line, recalculate every area, re-establish the entire map of the agricultural landscape. They did this year after year, century after century, and they got very, very good at it. The Greek historian Herodotus, writing in the 5th century BC, described these surveyors and called what they did geometria. Geo, meaning earth, and metria, meaning measurement. Geometry, the measuring of the earth. That is where the word comes from, and it is worth remembering, because geometry did not start as an abstract intellectual exercise.
It started as a desperately practical activity, performed by people standing in muddy fields with ropes and stakes, trying to figure out the shape and size of irregular patches of land, so that the tax collector would not cheat anyone and nobody would start a fight. The Egyptians measured using their bodies. A cubit was the length from the elbow to the fingertips, roughly 18 inches. A palm was the width of a hand. They would stretch ropes marked in cubits across a field and use them to calculate areas. For rectangular fields, this was straightforward, length times width. But fields were rarely perfect rectangles, and the Egyptians developed methods for approximating the areas of triangles, trapezoids, and even circles. The circle calculation is particularly impressive. In problem 50 of the Rind Papyrus, the scribe Arms describes a method for finding the area of a circle that amounts to taking the diameter, subtracting 1/9 of it, and squaring the result.
If you work out what value of pi this implies, you get about 3.16, which is less than 1% off from the true value. For practical purposes, for figuring out how much grain fits in a circular granary, that is more than accurate enough. But the Egyptians also knew something about triangles that would turn out to be far more significant. Their surveyors discovered that if you take a rope and tie knots at intervals of 3, 4, and 5 units, then stretch it into a triangle, you get a perfect right angle, every time. The 3-4-5 triangle always produces a 90-degree corner. They used this constantly for laying out foundations, for squaring up buildings, for orienting the pyramids. The Great Pyramid at Giza, built around 2500 BC, has a base that is almost perfectly square, with sides of about 756 feet, and the 4 corners are aligned to the cardinal directions with astonishing precision.
You do not achieve that without a deep working knowledge of right angles and their properties. But here is the key limitation of Egyptian geometry. The Egyptians knew that the 3-4-5 rope trick worked. They could demonstrate it, use it, rely on it. But they never asked why it worked. They never proved that all right triangles share this property, that for any right triangle, the square on the longest side equals the sum of the squares on the other two. They solved specific problems with specific numbers, They verified their answers by plugging the results back in and checking. But they did not generalize, and they did not prove. The leap from knowing that something works to understanding why it must work, that leap happened in Greece, and it changed everything. Now, the standard story says that Greek mathematics began with Thales of Miletus, who lived around 600 BC. Thales is traditionally credited with being the first person to prove a mathematical statement, to construct a logical argument demonstrating that something must be true, rather than merely observing that it appears to be true. He is said to have proved that a circle is bisected by its diameter, that the base angles of an isosceles triangle are equal, and several other geometric facts. Whether Thales himself actually proved these things in the rigorous sense we mean today, we cannot say for certain. We have no surviving writings from Thales. Everything we know about him comes through later authors writing centuries after his death, and by that time, legend and fact had become thoroughly tangled. But the broader point is solid. Somewhere around the 6th century BC, Greek mathematicians began demanding a new standard of certainty. They were not satisfied with knowing that a mathematical fact was practically useful. They wanted to know that it was logically necessary.
And the person who crystallized this new approach more than anyone else was Pythagoras. We already met him in the last chapter when we talked about the crisis of irrational numbers. But Pythagoras's influence goes far beyond that one discovery. He and his followers established the idea that mathematics was not just a collection of useful tricks. It was a way of understanding reality at the deepest level. The Pythagoreans discovered that musical harmony was mathematical. A string half as long produces a note an octave higher. A string 2/3 as long produces a perfect fifth. A string 3/4 as long produces a perfect fourth. Clean, simple ratios. And the Pythagoreans extrapolated wildly from this. If music is mathematical, they reasoned, then perhaps everything is. Perhaps the entire universe runs on number and proportion. They believed this with an intensity that was religious in character, and their community operated more like a cult than a school. But the mathematical legacy is real and enormous. The Pythagoreans are credited with the theorem that bears their name, the proof that in any right triangle, the square of the hypotenuse equals the sum of the squares of the other two sides. We talked about how the Babylonians knew the relationship as an empirical fact. What the Pythagoreans added was the proof, a logical argument demonstrating that this must be true for every right triangle, not just the ones you happen to measure. Every single one. An infinite number of triangles, all obeying the same rule, and you can know this without measuring any of them. That shift, from "we have checked a lot of cases and it seems to work" to "here is why it must always work," is the revolution. It is the single most important conceptual breakthrough in the history of mathematics. Because once you have proof, you have certainty. And mathematical certainty is different from every other kind of certainty humans possess. Scientific theories can be overturned by new data. Historical accounts can be revised. Philosophical arguments can be countered. But a mathematical proof, once established, is permanent. The Pythagorean theorem was true in 500 BC. It is true now. It will be true in 1 billion years. It was true before anyone discovered it. There is something almost eerie about that kind of permanence. The Greek geometric tradition reached its highest expression about 2 centuries after Pythagoras, in the work of a man named Euclid. Euclid worked in Alexandria, Egypt, around 300 BC, during the reign of the first Ptolemaic pharaohs, in a city that was rapidly becoming the intellectual capital of the Mediterranean world. And what Euclid created was arguably
the most influential textbook in human history. It is called The Elements. 13 books covering plane geometry, solid geometry, number theory, and the theory of proportions. Euclid probably did not discover most of the mathematics in it. He was a compiler, an organizer, a systematizer of extraordinary genius. What made the Elements revolutionary was not its content, but its structure. Euclid began with definitions, postulates, and common notions. A point is that which has no part. A line is breadthless length. Two things equal to the same thing are equal to each other. These starting assumptions were deliberately chosen to be as simple and self-evident as possible. And then, from these bare foundations, Euclid built everything else through pure logical deduction. Each proposition was proved using only the definitions, the postulates, the common notions, and previously proved propositions. Nothing was assumed that had not been established. Nothing was hand-waved. The logical chain was unbroken from start to finish. The Elements was used as a textbook for more than 2,000 years. Abraham Lincoln studied it. Einstein studied it. It has been printed in more editions than any book except the Bible. And its influence goes far beyond mathematics. The structure of the Elements, the idea of starting with axioms and deriving everything through logical deduction, became a model for rigorous thinking in philosophy, science, law, and theology. When Thomas Jefferson wrote in the Declaration of Independence that we hold these truths to be self-evident, and then derived political conclusions from them, he was, consciously or not, following Euclid's method. But Euclid's fifth postulate, the one about parallel lines, was always a little bit different from the other four. The first four postulates are simple and feel almost obvious. You can draw a straight line between any 2 points. You can extend a line indefinitely. You can draw a circle with any center and radius. All right angles are equal. These feel like natural, unavoidable truths. The fifth postulate is more complicated. It says, essentially, that given a straight line and a point not on that line, there is exactly one line through the point that is parallel to the original line. This sounds reasonable, and it matches our everyday experience. But it is a more complex statement than the other four, and from the very beginning, mathematicians felt uneasy about it. Many suspected it was not really a postulate at all, that it ought to be provable from the first four. If you could prove the fifth postulate as a theorem, you could simplify Euclid's foundations. For more than 2,000 years, mathematicians tried. And for more than 2,000 years, they failed. Ptolemy tried in the 2nd century. Proclus tried in the 5th century. The great Islamic mathematicians Omar Khayyam and Nasir al-Din al-Tusi tried in the 11th and 13th centuries. The Italian Jesuit Giovanni Saccheri tried in the 18th century. All of them failed, and the failures were always the same.
They would assume the fifth postulate was false, try to derive a contradiction, and instead end up with a collection of strange but perfectly consistent results. Results that described a geometry unlike anything they had ever imagined, but that was internally coherent. And then, in the early 19th century, 3 mathematicians, working independently and in different countries, realized why everyone had failed. The fifth postulate could not be proved from the other 4 because it was genuinely independent of them. You could replace it with a different statement and still get a perfectly consistent geometry. A different geometry, a non-Euclidean geometry, but one with no internal contradictions. The first to see this clearly was Carl Friedrich Gauss.
widely considered the greatest mathematician since antiquity. Gauss worked out the theory of non-Euclidean geometry in the early 1800s, but did not publish it, reportedly because he feared the controversy it would cause. He called it the howling of the Boeotians, referring to the ancient Greeks' contempt for the supposedly uncultured Boeotians. He did not want to deal with the intellectual firestorm. Independently, a young Hungarian mathematician named János Bolyai developed the same ideas and published them in 1832 as an appendix to a book written by his father. And independently again, a Russian mathematician named Nikolai Lobachevsky published a similar theory in 1829. What they had discovered was that you could replace Euclid's fifth postulate with the statement that, through a point not on a line, there are infinitely many lines parallel to the original, and the resulting geometry was perfectly consistent. In this geometry, the angles of a triangle add up to less than 180 degrees. Parallel lines diverge. The space curves like a saddle. It is called hyperbolic geometry, and it is every bit as logically valid as the flat Euclidean geometry you learned in school. You could also go the other direction and say that through a point not on a line, there are no parallel lines at all. This gives you elliptic geometry, where the angles of a triangle add up to more than 180 degrees. Parallel lines do not exist, and the space curves like the surface of a sphere. Think about lines of longitude on a globe. They are all parallel at the equator, but they all meet at the poles. On a sphere, there are no parallel lines. This was a profound shock to the intellectual world. For more than 2,000 years, Euclidean geometry had been regarded as the truth about space, the one and only correct description of the physical world. Now it turned out there were alternative geometries, and mathematics alone could not tell you which one described reality.
That was an empirical question, a question about the actual shape of the universe, not a question that could be settled by pure thought. And here is where the story takes a turn that nobody could have predicted. About 30 years after Bolyai and Lobachevsky published their work, a German mathematician named Bernhard Riemann delivered a lecture in 1854 that would reshape humanity's understanding of space itself. Riemann was only 27 years old, shy, and so nervous about public speaking that he reportedly had a terrible time preparing for the lecture. But what he presented that day was one of the most far-reaching pieces of mathematics ever created. Riemann generalized the idea of non-Euclidean geometry into a framework that could describe spaces of any number of dimensions, with curvature that could vary from point to point. In Riemann's framework, space could be flat here and curved there, positively curved in one region and negatively curved in another.
The curvature could change smoothly, flowing like a landscape. Riemann built the mathematical tools for this, the entire apparatus of what we now call Riemannian geometry. And then he essentially put it on the shelf. It was beautiful mathematics, but he had no particular application in mind. It was a theoretical framework waiting for a physical theory to inhabit it. The wait lasted about 60 years. In 1915, Albert Einstein published his general theory of relativity, and it turned out that the mathematics he needed, the language in which the theory of gravity had to be written, was Riemannian geometry. Einstein showed that gravity is not a force pulling objects toward each other, as Newton had described. Gravity is the curvature of space-time caused by the presence of mass and energy. Massive objects like stars and planets warp the geometry of space around them, and other objects follow the curves in that warped space, which is why planets orbit stars and why you stay on the surface of the Earth. The geometry of the actual universe, the physical space you and I live in, is not Euclidean. Space is curved, not in some metaphorical or approximate sense, but literally, measurably, verifiably curved. Light bends around massive objects.
Clocks run slower in strong gravitational fields. GPS satellites have to account for the curvature of space-time to give you accurate positions. If they used Euclidean geometry, your GPS would drift by about 7 miles per day.
And the mathematical framework that describes all of this, that makes GPS work, and that predicts black holes and gravitational waves, was built by Bernhard Riemann 60 years before Einstein needed it. By a mathematician who was just following the shapes wherever they led, with no idea that his abstract constructions would turn out to describe the actual shape of reality. This is one of the deepest mysteries in all of science. Why does mathematics work? Why do abstract structures, invented by human beings for purely intellectual reasons, keep turning out to be exactly the right tools for describing the physical universe? The physicist Eugene Wigner wrote a famous essay in 1960 about what he called the unreasonable effectiveness of mathematics in the natural sciences. Nobody has a satisfying answer. Maybe we are discovering structures that genuinely exist in nature. Maybe we are inventing structures and finding that some of them happen to fit. Maybe mathematics is just what pattern recognition looks like when it is done very carefully. Whatever the reason, the history of geometry is full of these moments where pure mathematical exploration, pursued for its own sake, produces tools that turn out to be indispensable for understanding reality. Let me give you one more example, because it is too beautiful to skip. Around 220 BC, a Greek mathematician named Apollonius of Perga wrote an exhaustive treatise on conic sections, the curves you get when you slice a cone with a flat plane at different angles. Cut it horizontally, and you get a circle. Cut it at an angle, and you get an ellipse. Cut it parallel to the side of the cone, and you get a parabola. Cut it even steeper, and you get a hyperbola. Apollonius classified these curves, studied their properties, worked out their equations. It was brilliant, detailed, thoroughly abstract work. He was not trying to solve any practical problem.
He was just fascinated by the shapes. Fast forward about 1800 years. In the early 1600s, Johannes Kepler was poring over the astronomical data left behind by the Danish astronomer Tycho Brahe, trying to figure out the exact shape of Mars's orbit around the Sun. Everyone assumed planetary orbits were circles because circles were perfect, and surely the heavens would arrange themselves in perfect shapes. But the data did not fit. Kepler tried circles. He tried combinations of circles. Nothing worked. And then, after years of painstaking calculation, he discovered that the orbit of Mars is an ellipse, with the Sun at one focus. An ellipse, one of Apollonius's conic sections, a shape that had been studied and classified 1800 years earlier for no practical reason at all. Apollonius had no idea his curves would describe the paths of planets. Kepler had no idea that a 2200-year-old piece of pure mathematics would give him the key to understanding the solar system. The mathematics was sitting there, patient and complete, waiting for someone to realize what it was for. But let me return to Archimedes, because his story deserves more time. Archimedes of Syracuse, who lived from about 287 to 212 BC, was arguably the greatest mathematician of the ancient world, and maybe of any world. He was born in Syracuse on the island of Sicily, and he seems to have spent most of his life there, though he may have studied in Alexandria as a young man. Archimedes combined mathematical brilliance with a practical inventiveness that was almost unmatched. He is said to have designed war machines that defended Syracuse against a Roman siege for nearly 2 years. Cranes that could reach over the city walls, grab Roman ships, and flip them into the sea. Catapults that hurled massive stones.
According to some accounts,
He even designed a system of mirrors to focus sunlight on the Roman fleet and set the ships on fire, though most historians think this particular story is a later embellishment. But Archimedes' real legacy is mathematical. He calculated the area under a parabolic arch and showed it is exactly 2/3 of the area of the enclosing rectangle. He found the surface area and volume of a sphere and showed that the volume is exactly 2/3 the volume of the circumscribing cylinder. This result moved him so deeply that he requested a sphere inscribed in a cylinder be carved on his tombstone. When the Roman general Cicero visited Syracuse more than a century after Archimedes' death, he found the tomb overgrown with vegetation and identified it by this very carving. Archimedes approximated pi with remarkable precision. He inscribed a polygon inside a circle and circumscribed another polygon outside it.
The circle's circumference must be between the perimeters of the inner and outer polygons. By using polygons with 96 sides, he narrowed pi down to between 3 and 10/71 and 3 and 1/7. Converting to decimals, that is roughly between 3.1408 and 3.1429. The true value is 3.14159. Archimedes pinned it down to better than 1 part in 1,000 using nothing but geometric reasoning. His method of exhaustion, where you approximate a curved region by filling it with ever finer polygonal pieces, is essentially the idea behind integral calculus. Archimedes was doing integration almost 2,000 years before Newton and Leibniz gave it a name. The only thing he lacked was the algebraic notation and the concept of a limit that would allow the method to be formalized and generalized. The death of Archimedes is one of the most famous stories in the history of science.
In 212 BC, the Romans finally breached the walls of Syracuse after a 2-year siege. According to the historian Plutarch, a Roman soldier came upon Archimedes, who was drawing geometric diagrams in the sand, absorbed in a mathematical problem. The soldier ordered him to come along. Archimedes reportedly said, "Do not disturb my circles." The soldier killed him. Whether this story is literally true, we cannot know. But its persistence tells you something about how the ancient world viewed Archimedes. He was a man so devoted to mathematical truth that he could not be distracted from it even by the fall of his city. And the work he left behind, fragmentary as it is, influenced mathematics for centuries. Now, when we talk about the Greek geometric tradition, we should also acknowledge a figure who often gets overlooked. Hypatia of Alexandria, who lived from about 355 to 415 AD, was one of the last great mathematicians of the ancient world and one of the earliest known women mathematicians. She taught at the Neoplatonic school in Alexandria, where she lectured on mathematics, astronomy, and philosophy. She wrote commentaries on the works of earlier mathematicians, including Diophantus and Apollonius, and she was respected as a leading intellectual figure in the city. Hypatia was murdered in March of 415 by a mob of Christian zealots who dragged her from her chariot, beat her to death with roofing tiles, and mutilated her body. The reasons for her murder are complex and debated, tangled up with politics, religion, and the power struggles of late Roman Alexandria. But her death is often cited as a marker of the end of the classical tradition of learning in the Mediterranean. The great library of Alexandria, already diminished by this time, would not survive much longer. An era of mathematical and philosophical inquiry was drawing to a close. But mathematical knowledge did not die with the ancient world. It migrated. Greek texts were translated into Arabic by scholars working in the House of Wisdom in Baghdad during the 8th and 9th centuries. Islamic mathematicians preserved, extended, and transmitted this knowledge, adding their own innovations along the way. and eventually, through translation into Latin, and through direct contact during the Crusades, and through the cultural exchanges of medieval Spain, this knowledge flowed back into Europe, sparking the Renaissance and everything that followed. The Islamic contribution to geometry deserves special mention. Omar Khayyam, the Persian poet who wrote the Rubaiyat, was also a serious mathematician. Working in the 11th century, he made significant progress on the problem of the parallel postulate, coming very close to the insights that would later lead to non-Euclidean geometry.
He also developed geometric methods for solving cubic equations, using the intersections of conic sections to find solutions. This was a brilliant synthesis of algebra and geometry, centuries before Descartes would formalize the connection. Nasir al-Din al-Tusi, working in the 13th century, also made important contributions to geometry and trigonometry. He was the first to treat trigonometry as a subject independent of astronomy, giving it its own systematic foundations. His work on the parallel postulate influenced later European mathematicians and contributed to the eventual discovery of non-Euclidean geometry. Let me also spend a moment on topology, because it represents a fundamentally different way of thinking about shape that has become one of the most active areas of modern mathematics. Topology was born in the 18th century with a puzzle that seems almost playful. The city of Königsberg in Prussia was built on both sides of a river and included 2 islands.
7 bridges connected the various parts of the city. The residents wondered whether it was possible to walk through the city, crossing each bridge exactly once, and return to your starting point. In 1736, Leonhard Euler proved that it was not possible, and in doing so, he founded the field we now call topology, although it would not get that name until much later. Euler's key insight was that the specific shapes and sizes of the landmasses did not matter. What mattered was the pattern of connections, which pieces of land were connected to which by bridges. He abstracted away all the geometric details and focused purely on the structure of the connections. Topology is sometimes described as rubber sheet geometry. It studies the properties of shapes that are preserved when you stretch, bend, twist, or deform them, but do not tear or glue. A coffee cup and a donut are topologically the same object because you can smoothly deform one into the other.
Both have exactly one hole. A sphere and a cube are topologically the same because you can round off the corners of the cube and inflate it into a sphere without tearing anything. But a sphere and a donut are topologically different because the donut has a hole and the sphere does not, and you cannot create or destroy a hole by stretching and bending alone. This seems like an odd thing to study, but topological ideas turn out to be extraordinarily powerful. The Poincaré conjecture, proposed by Henri Poincaré in 1904, asked whether any closed 3-dimensional shape in which every loop can be continuously shrunk to a point must be topologically equivalent to a 3-dimensional sphere. It was one of the great open problems in mathematics for nearly a century, and its eventual solution, by a reclusive Russian mathematician who then turned down every prize the world offered him, is a story we will come back to before the night is over.
Now, I have been telling the story of geometry as if it lived entirely in the world of shapes and physical space. But one of the most important moments in the history of mathematics was the moment when geometry and arithmetic, shapes and numbers, were fused together. And the person who did it was a French philosopher-soldier named René Descartes. In 1637, Descartes published a work called La Géométrie as an appendix to his philosophical masterpiece, Discourse on the Method. And in it, he did something deceptively simple but enormously powerful. He introduced a coordinate system, 2 perpendicular number lines, a horizontal one and a vertical one, crossing at a point called the origin. Every point on a flat surface could now be identified by 2 numbers, its horizontal distance and its vertical distance from the origin.
A circle could be described by an equation. A line could be described by an equation.
Every geometric shape had an algebraic expression, and every algebraic expression had a geometric shape. This fusion, called analytic geometry, or Cartesian geometry after Descartes, broke down the wall between algebra and geometry. Problems that were hard to solve geometrically could be translated into algebra and solved with equations. Problems that were hard to solve algebraically could be visualized as geometric shapes. Two entire branches of mathematics, developed separately for thousands of years, were suddenly revealed to be two views of the same thing. And this is worth sitting with for a moment. The mathematical notation we use today, the symbolic language of x's and y's and equal signs and plus signs, feels so natural that it is easy to forget it was invented. It did not always exist. For most of the history of mathematics, equations were written out in words. The Babylonians described their procedures as verbal recipes.
The Greeks reasoned about relationships using geometric diagrams. The Arabic algebraists wrote everything as flowing prose. Diophantus, working in Alexandria around 250 AD, introduced some abbreviations, but his notation was still mostly verbal. Brahmagupta used abbreviations for different unknowns, naming them after colors. The modern symbolic notation began to emerge in the 15th and 16th centuries in Europe. The plus and minus signs appeared in German commercial arithmetic texts around 1489. The equals sign was introduced by the Welsh mathematician Robert Recorde in 1557. He chose two parallel horizontal lines because, as he wrote, no two things can be more equal. François Viette, working in the late 16th century, introduced the practice of using letters to represent unknown and known quantities, using vowels for unknowns and consonants for known values.
Descartes, in 1637, settled on the convention we still use, using letters from the end of the alphabet for unknowns and letters from the beginning for constants. These notational choices matter far more than they might seem. Good notation makes certain operations easy to perform and certain patterns easy to see. Leibniz's calculus notation, with its dy over dx and its elongated s for integration, suggested algebraic manipulations that turned out to be valid and powerful. Newton's dot notation, while fine for certain purposes, did not suggest these manipulations as naturally. The English mathematicians who loyally used Newton's notation found themselves at a disadvantage compared to their continental colleagues, who used Leibniz's more suggestive symbols. The English mathematicians who loyally used Newton's notation found themselves at a disadvantage compared to their continental colleagues, who used Leibniz's more suggestive symbols. Notation is not just a way of recording mathematics. It is a tool for thinking. And the right notation can open doors that the wrong notation keeps closed.
And this fusion would turn out to be essential for the next question, the question that would dominate mathematics from the 17th century onward. Because, until Descartes, mathematicians had primarily studied things that held still. Fixed numbers, rigid shapes, static relationships. But the physical world is not static. Things move, they grow, they change. Planets sweep through curved orbits. Cannonballs arc through the air. Populations rise and fall. Temperatures fluctuate. The amount of daylight varies from season to season. Everywhere you look, quantities are in motion. And the question of how to deal mathematically with things that are constantly changing, how to pin down the behavior of something that refuses to hold still, that question would require an entirely new kind of mathematics. A mathematics of change, a mathematics so powerful that it would become the language of physics, engineering, economics, and virtually every science.
A mathematics whose invention would spark one of the most bitter priority disputes in intellectual history. A feud between two of the greatest minds who ever lived that would poison relations between English and continental mathematics for a century. That story begins with an apple, a plague, and a 23-year-old who went home to his mother's farm because the university was closed, and who, in the space of about 18 months, essentially reinvented the world. The year is 1665. England is being ravaged by plague, the bubonic plague. The same disease that killed a third of Europe 3 centuries earlier is sweeping through London. The death toll will eventually reach about 100,000. The city is shutting down. Cambridge University has closed its doors and sent its students home. Among those students is a 23-year-old named Isaac Newton. He has just finished his undergraduate degree and shows to this point no particular sign of genius. He is quiet, solitary, and obsessive. The kind of person who can disappear into a problem for days and forget to eat. He goes home to his mother's farm in Woolsthorpe, Lincolnshire, a small stone house in the English countryside. And there, over the next 18 months or so, while the plague burns through the population, he works. What Newton accomplishes during this period is almost impossible to believe. In the space of about a year and a half, working alone, with no teachers or collaborators, he develops the foundations of calculus, works out the basic principles of optics, and begins formulating his theory of gravity. Any one of these achievements would have made him one of the great scientists of his century. He did all 3 before he turned 25. He later called it his annus mirabilis, his year of miracles, although it actually stretched over closer to 2 years. The key insight, the one that concerns us tonight, was calculus. And to understand what Newton invented and why it mattered, you need to understand the problem he was trying to solve. The world moves. Planets orbit the sun. Arrows fly through the air. Water flows downhill. A ball thrown into the air rises, slows, stops, and falls back down. All of these involve quantities that are constantly changing. The position of the ball changes with time. Its speed changes with time. The speed of the change itself changes with time because the ball decelerates on the way up and accelerates on the way down. Now, mathematicians before Newton could handle static situations beautifully. They could calculate the area of a fixed shape. They could solve equations relating fixed quantities. But the moment things started moving, the old tools broke down. How do you calculate the exact speed of a falling object at a single instant? Speed is distance divided by time, but at a single instant, no distance has been covered and no time has elapsed. You are dividing 0 by 0, which is meaningless. And yet the object clearly has a speed at every instant. A dropped ball is moving faster after 2 seconds than after 1 second. There must be a definite speed at each moment. But how do you calculate it? The ancient Greeks had struggled with this. Zeno of Elea in the 5th century BC posed a series of famous paradoxes about motion. In one, he argued that an arrow in flight is actually motionless. At each instant of time, the arrow occupies a definite position. At that instant, it is not moving, because an instant has no duration. But if the arrow is motionless at every instant, and time is made up of instants, then the arrow never moves. The arrow clearly does move, so something is wrong with the argument. But for centuries, nobody could say exactly what. Archimedes working in the 3rd century BC, came closer than anyone in the ancient world to cracking this problem. He developed a technique called the method of exhaustion, which involved approximating curved areas by filling them with smaller and smaller polygons. Want to find the area of a circle? Inscribe a square inside it, then an octagon, then a 16-sided polygon, then a 32-sided polygon. Each one fits the circle more closely than the last. The areas of the polygons get closer and closer to the true area of the circle, and by pushing this process far enough, you can pin down the area to any desired precision. Using this technique, Archimedes pinned down the area under a parabola, the volume of a sphere, and the value of pi to extraordinary precision, all the results we talked about earlier. And as we noted, his method of exhaustion is essentially the idea behind integral calculus, performed 2,000 years early. What Archimedes was doing was, in essence, integration. He was summing up infinitely many infinitely small contributions to get a finite total. But he never formalized the process. He never turned it into a general method that could be applied systematically to any problem. And crucially, he never connected it to the question of rates of change. The relationship between finding areas and finding speeds, between integration and differentiation, would remain hidden for almost 2,000 years. Through the medieval period and the Renaissance, various mathematicians chipped away at pieces of the puzzle. Indian mathematicians of the Kerala school, working in the 14th and 15th centuries, discovered infinite series for trigonometric functions that anticipate results usually attributed to European mathematicians centuries later. They understood the idea of summing infinite series and could calculate pi to extraordinary precision using these methods.
Madhava of Sangamagrama, who lived around 1350 to 1425, is sometimes called the founder of mathematical analysis, and there is a strong case for it. In Europe, Pierre de Fermat and Descartes, in the early 17th century, developed methods for finding tangent lines to curves, which is essentially the problem of computing instantaneous rates of change. Bonaventura Cavalieri introduced a method of indivisibles that was a forerunner of integration. John Wallis contributed new techniques for computing areas. The pieces were coming together, but nobody had unified them into a single, coherent framework. Newton did. During that extraordinary period at Woolsthorpe, Newton developed what he called the method of fluxions. His core insight was that finding rates of change and finding areas are inverse operations. If you know how fast a quantity is changing at every moment, you can add up all those tiny changes to find the total accumulated change, which is like finding an area under a curve. And if you know the area under a curve, you can figure out how fast that area is growing at each point, which gives you the rate of change. This relationship, the fundamental theorem of calculus, is the conceptual backbone of the entire subject. It says that differentiation and integration are not just related, they are opposite sides of the same coin. And this connection transforms both of them from difficult one-off calculations into a systematic, almost mechanical process. To understand differentiation, Newton's approach to instantaneous rates of change, think about it this way. You want to know the speed of a ball at a single instant, let's say exactly 2 seconds after you drop it. You cannot measure speed at an instant directly, because speed requires some elapsed time and some covered distance.
But you can measure average speed over a short time interval. How far did the ball fall between 2 seconds and 2.1 seconds? Divide that distance by the time, 0.1 seconds, and you get an average speed. Now shorten the interval. How far did the ball fall between 2 seconds and 2.01 seconds? That gives a better approximation. between 2 seconds and 2.001 seconds, even better. As the interval gets smaller and smaller, the average speed gets closer and closer to some definite value. That value is the instantaneous speed at the 2-second mark. Newton figured out how to compute this limiting value directly, without having to go through the tedious process of evaluating shorter and shorter intervals. He developed rules, algorithms, that let you take a mathematical expression describing a quantity's behavior and immediately write down an expression for its rate of change. But here was the problem. Newton's method involved dividing by quantities that were getting infinitely small, and then, at the end of the calculation, treating those quantities as if they were zero. This worked in the sense that it gave correct answers that matched observations. But logically, it was a mess. You cannot divide by something and then say it is zero. If it is zero, you divide it by zero, which is not allowed. If it is not zero, you cannot just discard it at the end. Newton himself was uneasy about this. He tried different ways of justifying the procedure, using geometric arguments, using physical intuition about motion, using the concept of quantities flowing toward their limits. But he never fully resolved the logical difficulty.
And when he published his masterwork, the Principia Mathematica, in 1687, he actually presented most of his results using classical geometric proofs rather than calculus, partly because he knew the logical foundations of calculus were shaky, and he did not want his physics to be rejected because of doubts about his mathematics. Meanwhile, in Germany, a man named Gottfried Wilhelm Leibniz was developing the same ideas independently. Leibniz was a polymath, a philosopher, a diplomat, a logician, and a mathematician. He came to calculus from a different direction than Newton, focusing more on the notation and the algebraic manipulation of infinitesimal quantities. And it was Leibniz who gave us the notation we still use today, the elongated S for integration, the dy over dx for derivatives, the clean, elegant symbolic language that makes calculus teachable and workable. Leibniz published first. His first paper on calculus appeared in 1684.
Newton had developed his method earlier, probably by 1666, but had shared it only in private correspondence and unpublished manuscripts. When Leibniz published, Newton was furious. He accused Leibniz of having seen his unpublished notes and stealing the ideas. Leibniz denied it. The dispute escalated into one of the ugliest feuds in the history of science, with each man's supporters attacking the other in pamphlets, letters, and official pronouncements. The Royal Society of London, of which Newton was president, conducted an investigation and concluded that Newton had priority, but the investigation was widely regarded as biased, and Leibniz's reputation on the continent remained intact. The modern consensus is that Newton and Leibniz developed calculus independently. They were both drawing on the same body of prior work, they were both brilliant enough to see the synthesis, and they arrived at the same destination by different routes.
Newton's approach was more geometric and physical, motivated by problems about motion and forces. Leibniz's approach was more algebraic and symbolic, motivated by the desire for a general-purpose calculating tool. The feud had real consequences. English mathematicians, loyal to Newton, insisted on using Newton's notation and methods. Continental mathematicians used Leibniz's, and Leibniz's notation was simply better, more flexible, more suggestive of the right manipulations. For about a century, English mathematics fell behind the continent, partly because of this stubborn loyalty to inferior notation. Symbols matter. The way you write mathematics shapes the way you think about it. But regardless of the priority dispute, the important thing is that calculus worked. It worked spectacularly. Within decades of its invention, it was being used to calculate the orbits of planets, the trajectories of projectiles, the behavior of vibrating strings, the flow of fluids, the conduction of heat. It became the language of physics. Every equation of motion, from Newton's laws to Maxwell's equations of electromagnetism to Schrödinger's equation in quantum mechanics, is written in the language of calculus. Without it, modern science simply would not exist. And yet, for about 150 years after Newton and Leibniz, nobody could explain why calculus actually worked. Everyone agreed that the results were correct. The predictions matched observations with extraordinary precision. But the logical foundation was a mess. Calculus dealt with infinitely small quantities, infinitesimals, that were somehow not zero, but not any definite positive number either.
The philosopher George Berkeley, Bishop of Cloyne, published a famous attack on calculus in 1734, in which he asked whether these infinitesimals were the ghosts of departed quantities. He had a point. If mathematicians were going to demand logical rigor in other areas, they could not simply wave their hands when it came to the foundations of their most powerful tool. The resolution came gradually, through the work of several mathematicians in the early 19th century. The key figure was Augustin Louis Cauchy, a French mathematician working in the 1820s who reformulated calculus in terms of limits rather than infinitesimals. Instead of talking about infinitely small quantities, Cauchy talked about what happens as quantities approach a limit. The instantaneous speed of a falling ball at time t is the limit of the average speed over the interval from t to t plus h, as h approaches zero. You never actually set h equal to zero. You study what happens as h gets closer and closer to zero, and the limiting value is the answer. This sounds like a subtle distinction, and in some ways it is, but it made all the difference. Cauchy's approach, refined further by Carl Weierstrass later in the century, put calculus on a rigorous, logical foundation for the first time. The epsilon-delta definition of a limit, which every mathematics student learns and which many of them find torturous, was the price of making calculus honest. It replaced vague talk about infinitely small quantities with precise, unambiguous conditions that could be checked and verified. The irony is striking. Calculus was invented around 1665. It was not made rigorous until about 1821. For more than 150 years, one of the most powerful tools in all of mathematics rested on foundations that nobody could properly justify. The tool was built long before the ground it stood on was solid. And yet it worked. It worked so well that nobody was willing to stop using it just because the philosophy was questionable. Sometimes in mathematics, the doing runs ahead of the understanding, and the understanding has to catch up later. And catching up is what mathematicians spent much of the 19th century doing. The drive to make calculus rigorous led to an entire new branch of mathematics called analysis, which is essentially the study of limits, continuity, convergence, and the precise behavior of functions. Analysis is where you go when you want to understand exactly why calculus works, exactly when its methods are valid, and exactly what can go wrong when you are not careful. Along the way, analysts discovered that their intuitions about continuous functions could be badly wrong. In 1872, Carl Weierstrass constructed a function that is continuous everywhere, but differentiable nowhere.
a curve with no sharp corners, no jumps, no breaks, that nonetheless has no tangent line at any point. It is smooth in the sense of having no gaps, but infinitely jagged at every scale. If you zoom in, hoping to see it flatten out, it just gets jaggier. Always. Forever. This function was considered so monstrous when it was first presented that some mathematicians refused to accept it. Henri Poincaré called such functions a gallery of monsters. But the monsters were logically valid, and their existence forced mathematicians to be much more careful about what they assumed. Let me back up for a moment and give you a clearer picture of just how enormous the impact of calculus was once it was let loose on the world. Because Newton and Leibniz did not just solve a mathematical problem, they created a language. And once that language existed, it became possible to say things that could not be said before.
Within a generation of Newton's Principia, mathematicians were using calculus to attack problems that had been completely intractable. The Swiss mathematician Leonhard Euler, who was born in 1707 and who is widely regarded as the most prolific mathematician in history, took calculus and pushed it into every corner of mathematics. Euler was extraordinary. He published more than 800 papers and books during his lifetime, a rate of about one per week for the last 25 years of his career. And he did much of this work after losing the sight in one eye in his late 20s and then going completely blind in his 60s. Blindness barely slowed him down. He had an astonishing memory and could perform complex calculations in his head. Euler used calculus to study the vibrations of strings and the flow of fluids. He developed the theory of differential equations, equations that relate quantities to their rates of change into a systematic discipline. He introduced most of the notation we still use today: the letter E for the base of the natural logarithm, the letter I for the square root of -1, the Greek letter pi for the ratio of a circle's circumference to its diameter, the sigma notation for sums, the function notation f of x. If you have ever written f of x equals something, you are using Euler's notation. Euler also discovered what many mathematicians consider the most beautiful equation in all of mathematics. It is called Euler's identity, and it says that e raised to the power of I times pi plus 1 equals 0. This single equation connects the 5 most important numbers in mathematics, 0, 1, e, I, and pi, using only the operations of addition, multiplication, and exponentiation. 3 of these numbers, 0, 1, and pi, come from ancient mathematics. The number e comes from the study of growth and compound interest. The number I comes from the solution of polynomial equations. They arise in completely different contexts, from completely different motivations, and yet they are linked by this startlingly simple relationship. When you see it for the first time, it feels like you are looking at something that was always there, hidden in the structure of mathematics, waiting to be noticed. After Euler, the French mathematician Joseph Fourier made a discovery in the early 19th century that would prove equally revolutionary. Fourier was studying the conduction of heat, a practical problem motivated by the industrial needs of Napoleonic France. He showed that any function, any curve, no matter how irregular or complicated, can be decomposed into a sum of simple sine and cosine waves. Different frequencies, different amplitudes, all added together to recreate the original shape. This is an astonishing result if you think about it. It means that the language of waves is universal.
Any signal, any pattern, any variation can be expressed as a combination of simple oscillations. Fourier analysis, as it came to be called, became one of the most widely used tools in all of science and engineering. It is the mathematical foundation of signal processing, of audio compression, of image analysis. When your phone compresses a music file into MP3 format, It is using Fourier analysis to identify the frequencies that matter most and discard the rest. When an MRI machine constructs an image of your brain, it is using Fourier transforms to convert raw data into a picture. Fourier's mathematics, motivated by the humble problem of how heat spreads through a metal bar, became the backbone of the digital age. The 19th century also saw the development of probability theory and statistics into mature mathematical disciplines.
The basic ideas of probability go back much further, to Blaise Pascal and Pierre de Fermat, who worked out the foundations in the 17th century while analyzing games of chance. A French nobleman named Antoine Gombeau, who went by the title Chevalier de Méret, had posed a gambling problem to Pascal. If a game of chance is interrupted before it is finished, how should the stakes be divided fairly among the players, given the current state of the game? Pascal and Fermat exchanged letters about this problem in 1654, and their correspondence is traditionally regarded as the birth of probability theory. But it was in the 19th and 20th centuries that probability and statistics grew into the powerful tools we know today. Carl Friedrich Gauss developed the method of least squares for fitting curves to data and discovered the normal distribution, the famous bell curve that shows up everywhere in nature.
Whenever you see an average with most values clustered near it and fewer values farther away, the bell curve is at work. Human heights follow a bell curve. Test scores follow a bell curve. Measurement errors follow a bell curve. The ubiquity of this distribution is explained by the central limit theorem, which says that whenever you add up many small, independent random effects, the result tends toward a bell curve regardless of the underlying distributions of the individual effects. It is one of the most powerful and surprising results in all of mathematics. In the 20th century, probability became essential to physics through quantum mechanics. In the quantum world, the outcome of a measurement is not determined in advance. You cannot predict exactly where an electron will be found. You can only calculate the probability of finding it in a given location.
The wave function in quantum mechanics is essentially a probability distribution, and the rules for how it evolves over time are written in the language of calculus, specifically in the form of Schrödinger's equation. The mathematics of change and the mathematics of uncertainty brought together to describe the most fundamental level of physical reality. Let me also mention the mathematics of chaos, because it reveals something unexpected about the question of change. In the 1960s, a meteorologist named Edward Lorenz was running a simple computer model of atmospheric convection. The model consisted of just 3 coupled differential equations, nothing complicated. One day, he wanted to rerun a simulation, and to save time, he started it from the middle rather than the beginning, typing in the numbers from a printout. But the printout had rounded the numbers to 3 decimal places, while the computer stored them to 6.
The difference was tiny, less than 1 part in 1,000.
When Lorenz ran the simulation, the results diverged dramatically from the original run. Within a short time, the 2 solutions bore no resemblance to each other. A minuscule difference in starting conditions had led to a completely different outcome. Lorenz had stumbled onto what we now call sensitive dependence on initial conditions, or more popularly, the butterfly effect. The idea that a butterfly flapping its wings in Brazil could, through a chain of atmospheric interactions, trigger a tornado in Texas weeks later. This was not a flaw in the model. It was a genuine property of the equations. Deterministic systems, systems with no randomness whatsoever, could produce behavior that was effectively unpredictable, because any measurement, no matter how precise, introduces a tiny error. And in a chaotic system,
that error grows exponentially over time. After enough time, your prediction is no better than a guess.
Chaos theory revealed a deep tension in the mathematics of change. Calculus gives you equations that perfectly describe how a system evolves. In principle, those equations determine the future completely. But in practice, for chaotic systems, you cannot exploit that determinism because you can never know the initial conditions with perfect precision. The mathematics of change is exact. The predictions it generates are, in certain systems, inherently limited. Certainty and unpredictability coexist in the same equations. This was a humbling realization, and it connects to the deeper question of what mathematics can and cannot tell us about the world. Calculus is the most powerful tool humans have ever invented for understanding change. It has given us flight, space travel, modern medicine, telecommunications, everything that depends on understanding how things evolve over time. And yet there are systems, perfectly ordinary systems, described by perfectly simple equations, where the behavior is so sensitive to initial conditions that long-term prediction is fundamentally impossible. The mathematics of change is still evolving. Partial differential equations, which describe how quantities change across both space and time, remain one of the most active areas of research. The Navier-Stokes equations, which govern the flow of fluids, were written down in the early 19th century and are used every day by engineers and scientists. But the fundamental mathematical question of whether these equations always have smooth, well-behaved solutions, or whether they can develop singularities where the solution blows up to infinity in a finite time, remains unanswered. This is one of the 7 Millennium Prize problems, carrying a reward of $1 million, and it has been open since the equations were first formulated nearly 200 years ago.
So the question of what happens when things change started with Zeno's arrow and Archimedes' parabola. It passed through Newton's falling apples and Leibniz's elongated S. It was made rigorous by Cauchy and Weierstrass. It produced the tools that built the modern world, the differential equations that govern everything from bridges to smartphones to the orbit of the International Space Station. And it keeps generating surprises. The Navier-Stokes problem is still open. Chaos theory continues to reveal unexpected connections between simplicity and complexity. The mathematics of change is still changing. But throughout all of this, from the Greeks to the present day, there was always a deeper question lurking underneath. A question that the other 3 questions kept bumping into, kept needing, kept depending on without always acknowledging it. Why? Why must the Pythagorean theorem be true? Not just, does it seem to work, but can you prove it must be true for every right triangle, now and forever? Why must calculus give correct answers? Not just, does it match observations, but is the logical argument airtight? Why must Cantor's hierarchy of infinities hold up? Not just, is it beautiful, but is it certain? The question of why, the question of proof and certainty, and the limits of what we can know, is the deepest question in all of mathematics. And the story of how mathematicians pursued it, from the first logical arguments in ancient Greece, all the way to a devastating result that shook the foundations of human knowledge in 1931, is where we are going next. It involves a boy who died in a duel, a recluse
who refused $1 million, and a quiet Austrian who proved that the dream of perfect knowledge is forever out of reach. Let me tell you about a boy named Évariste Galois. He was born in 1811 in a small town near Paris, and from a very young age, it was clear that he was something unusual. At 15, he was reading original mathematical papers that most professional mathematicians would have found challenging. At 16, he was doing original mathematical research. At 17, he submitted a paper to the French Academy of Sciences that, he believed, solved one of the great open problems in mathematics. The paper was lost. He submitted another. It was rejected. He tried again. Rejected again. The mathematical establishment of Paris did not know what to make of him. His ideas were so far ahead of the conventions of his time that the referees could not follow his arguments. Simeon Denis Poisson, one of the leading mathematicians of the era, read Galois' work and declared it incomprehensible. It was not incomprehensible. It was revolutionary. But revolutions are hard to recognize from the inside.
Galois was also politically radical, a passionate Republican in a time of monarchist restoration. He was arrested twice for political agitation. He was expelled from the École Normale Supérieure. His life was chaotic and frustrated, and it was about to end. On the morning of May 30th, 1832, Galois fought a duel. The circumstances are murky and have been endlessly debated. It may have been over a woman. It may have been politically motivated. Some have speculated that it was engineered by his political enemies. We will probably never know. What we do know is that the night before the duel, knowing that he might not survive, Galois stayed up writing. He wrote frantically, filling page after page with mathematical notes, results and ideas, scribbling in the margins, crossing things out, writing, "I have not time," next to several passages. He was trying to get as much as possible down on paper before dawn. He was shot in the duel the next morning and died the following day. He was 20 years old. The mathematics he wrote down that night, hastily and incompletely, but with stunning clarity of vision, contained the foundations of what we now call group theory. And group theory turned out to be one of the most important and far-reaching ideas in all of mathematics. It is the mathematics of symmetry, and it touches virtually every branch of modern mathematics and physics. But to understand what Galois was doing and why it matters, we need to back up and talk about the question of why. Because Galois was not just solving a problem, he was explaining, for the first time, why certain problems cannot be solved. And that question, the question of impossibility, turns out to be one of the most profound questions in mathematics. The story starts with equations.
Since the Babylonians, mathematicians had been solving equations, finding the value of an unknown quantity that makes an equation true. Linear equations, where the unknown appears to the first power, are straightforward. Quadratic equations, where the unknown is squared, were solved by the Babylonians and later formalized by the Arabs and Europeans. The quadratic formula, which every algebra student learns, gives you the solution to any quadratic equation in terms of its coefficients, using only addition, subtraction, multiplication, division, and square roots. In the 16th century, Italian mathematicians found similar formulas for cubic equations, equations with a cubed unknown, and quartic equations, equations with a fourth power unknown. The story of how those formulas were discovered is one of the juiciest dramas in the history of mathematics. In early 16th century Italy, a mathematician's reputation depended on winning public mathematical competitions. These were essentially intellectual duels, where mathematicians would challenge each other to solve lists of problems, and the loser would suffer professional humiliation. A professor named Scipione del Ferro, working in Bologna around 1515, discovered a method for solving a particular type of cubic equation. But he kept it secret, because in that competitive environment, a secret weapon was worth more than a published paper. He shared it only with a few trusted students, including one named Antonio Fior. After Del Ferro died, Fior decided to use the secret method to challenge a mathematician named Niccolò Fontana, better known as Tartaglia, which means the stammerer, a nickname he acquired after a childhood injury left him with a speech impediment. Fior thought he would easily defeat Tartaglia because he had the secret formula and Tartaglia did not. But Tartaglia was brilliant. When he saw the types of problems Fior was posing, he realized that a general method must exist. And in an intense period right before the competition, he independently discovered how to solve cubic equations. In the competition, Tartaglia solved all of Fior's problems. Fior could not solve any of Tartaglia's. It was a complete rout. Then, Girolamo Cardano, a doctor, mathematician, astrologer, and general Renaissance eccentric, entered the picture. Cardano was writing a comprehensive book on mathematics and wanted to include Tartaglia's method. He courted Tartaglia, flattering him, making promises, and eventually Tartaglia agreed to share his method under a solemn oath that Cardano would not publish it. But Cardano, together with his brilliant student, Lodovico Ferrari, extended Tartaglia's method to handle all types of cubics. And Ferrari went further and found a formula for quartic equations.
Then, in 1542, Cardano discovered that Del Ferro had actually found the cubic solution before Tartaglia, and he decided this freed him from his oath. In 1545, Cardano published Ars Magna, the Great Art, one of the most important mathematical works of the Renaissance. It contained the solutions to cubic and quartic equations. Cardano gave credit to Del Ferro, Tartaglia, and Ferrari, but Tartaglia was enraged. He felt betrayed. He published pamphlets attacking Cardano. Ferrari responded with pamphlets defending his teacher. Eventually, Ferrari challenged Tartaglia to a public debate. Tartaglia accepted. On the first day, it became clear that Ferrari had a deeper mastery of the new algebra. That night, Tartaglia fled Milan and never returned. His reputation was destroyed. This extraordinary drama gave mathematics the solutions to third and fourth degree equations. But it immediately raised a question. What about fifth degree equations?
What about equations where the unknown appears to the fifth power? Surely, given enough ingenuity, someone would find a formula for those too. For nearly 300 years, mathematicians tried, and for nearly 300 years, they failed. In 1824, a young Norwegian mathematician named Niels Henrik Abel proved something that nobody expected. He proved that no formula of the type used for quadratics, cubics, and quartics, no expression involving only addition, subtraction, multiplication, division, and root extraction, can solve the general fifth-degree equation. Such a formula simply does not exist. The problem is not that nobody has found it yet. The problem is that it is logically impossible. This was a conceptual earthquake. For the first time in the history of mathematics, someone had proved that a problem could not be solved. Not that it was very hard, not that current methods were insufficient, that it was impossible, period, forever, end of story. Abel died in 1829 at the age of 26 of tuberculosis, just days before a letter arrived offering him a prestigious position. His proof of impossibility was one of the great achievements of the 19th century. But it left an obvious question hanging. Why? Why can you solve fourth-degree equations, but not fifth-degree ones? What is it about the number 5 that makes the difference? This is the question Galois answered in those frantic pages the night before his duel. And his answer was astonishingly deep. He showed that the solvability of an equation is determined by the symmetry structure of its solutions. Each equation has an associated group of symmetries, the set of ways you can permute the solutions without changing the fundamental relationships between them. And the equation can be solved by radicals if and only if this symmetry group has a particular structural property, a property that Galois defined and that we now call solvability.
For equations of degree 4 or less, the symmetry groups always have this property. For equations of degree 5 and above, they generally do not. The obstruction is not a lack of cleverness, it is a structural feature of the symmetries involved. Galois had not just proved that fifth-degree equations are unsolvable by radicals. He had explained why, and in doing so, he had invented an entirely new way of thinking about mathematics. Group theory, the theory Galois created, is the study of symmetry in its most abstract form. A group is a collection of operations that can be combined and reversed. The rotations of a square form a group. The permutations of a set of objects form a group. The symmetries of a crystal form a group. The transformations that leave the laws of physics unchanged form a group. Wherever there is symmetry, there is a group lurking behind it. And symmetry, it turns out, is everywhere.
In the 20th century, group theory became the language of fundamental physics. The standard model of particle physics, our best description of the basic forces and particles that make up the universe, is built entirely on symmetry groups. Physicists predicted the existence of certain particles before they were observed because the mathematical structure demanded them. The symmetry groups had slots that needed filling. When those particles were later found in experiments, it was a stunning confirmation that abstract mathematics, developed to understand the solvability of polynomial equations, could predict the structure of physical reality. Galois could not have imagined quarks and gluons. But the abstract structures he sketched out by candlelight, the night before he was killed, turned out to be the scaffolding on which modern physics is built.
Now let me take you to another mathematician who reshaped our understanding of what mathematics can and cannot do, and who did so under very different circumstances. His name was Kurt Gödel, and his story is, in its own way, as dramatic as Galois'. By the early 20th century, mathematics was in the grip of what is sometimes called the foundational crisis. Cantor's set theory, which we talked about in the first chapter, had revealed that infinity is far stranger than anyone had imagined. But it had also exposed problems. In 1901, the British mathematician Bertrand Russell discovered a paradox at the heart of set theory that threatened to undermine the entire structure of mathematics. Russell's paradox is deceptively simple. Consider the set of all sets that do not contain themselves. Most sets do not contain themselves. The set of all cats is not itself a cat. The set of all prime numbers is not itself a prime number. So those sets belong in our collection. Now ask, does this collection contain itself? If it does, then by definition it should not, because it is supposed to contain only sets that do not contain themselves. But if it does not contain itself, then by definition it should, because it is a set that does not contain itself. Either way, you get a contradiction. A contradiction in mathematics is fatal, because from a contradiction, using the rules of logic, you can prove literally anything. If the foundations of mathematics allow contradictions, then the entire structure is worthless. Everything that has been proved becomes unreliable.
Russell's paradox showed that naive set theory, the intuitive version where you can define any set you want, is inconsistent. It can generate contradictions. This kicked off a period of intense soul-searching. How do you put mathematics on a solid foundation? How do you make sure the basic rules of the game do not lead to contradictions? Several camps emerged. The logicists, led by Russell himself and his collaborator Alfred North Whitehead, tried to reduce all of mathematics to pure logic. They spent years writing Principia Mathematica, a monumental work published between 1910 and 1913 that attempted to build mathematics from the ground up, using only logical axioms. It famously takes hundreds of pages before they can prove that 1 + 1 = 2. The work is an extraordinary intellectual achievement, but it is also extraordinarily unwieldy, and it did not fully accomplish what it set out to do. The formalists, led by David Hilbert, the most influential mathematician of the early 20th century, took a different approach. Hilbert wanted to treat mathematics as a formal game, played with symbols according to precise rules. The symbols do not need to mean anything. What matters is that the rules are consistent, that following them can never lead to a contradiction. Hilbert laid out an ambitious program.
Prove, using only simple and uncontroversial methods, that the formal systems of mathematics are consistent. If you could do that, you would know the foundations were solid, and mathematicians could go about their work with complete confidence. At the very moment Hilbert was articulating this program, a quiet young Austrian was about to demonstrate that it could never succeed. Kurt Gödel was born in 1906 in Brunn, in what was then Austria-Hungary and is now Brno in the Czech Republic. He studied at the University of Vienna, earned his doctorate at 23, and in 1931, at the age of 25, published a paper that is widely regarded as the most important result in mathematical logic, and possibly in all of mathematics ever. Gödel's incompleteness theorems. There are two of them, and together they draw a boundary around what mathematics can and cannot do, a boundary that is permanent and uncrossable. The first incompleteness theorem says this: in any consistent formal system that is powerful enough to describe basic arithmetic, there are true statements that cannot be proved within that system. Not statements that nobody has proved yet, statements that can never be proved, in principle, using the rules of that system. If the system is consistent, meaning it does not produce contradictions, then it is necessarily incomplete. There will always be truths that lie beyond the reach of its proofs. Let me try to give you the flavor of how Gödel proved this, because the method is almost as remarkable as the result. Gödel figured out a way to make arithmetic talk about itself. He assigned a unique number to every symbol, every formula, and every sequence of formulas, which means every proof in the formal system. This coding scheme, now called Gödel numbering, turned statements about proofs into statements about numbers. And then, using this encoding, Gödel constructed a specific arithmetic statement that effectively says, this statement is not provable in this system. Think about what happens. If the statement is provable, then it is true, which means it is not provable, which is a contradiction. So if the system is consistent, the statement cannot be provable. But if it is not provable, then what it says is true. It really is not provable, so it is a true statement that cannot be proved. The system is incomplete. This is not a deficiency of a particular system. It is not something you can fix by adding more axioms. If you add axioms to handle the unprovable statement, Gödel's argument constructs a new unprovable statement in the expanded system. You can never close all the gaps. There will always be more truths than any fixed set of axioms can capture. The second incompleteness theorem is even more devastating for Hilbert's program.
It says that a consistent system, powerful enough to describe basic arithmetic, cannot prove its own consistency. You cannot use mathematics to prove that mathematics is free of contradictions, at least not without stepping outside the system and using stronger assumptions that themselves need justification. Hilbert's dream of a complete self-verifying foundation for mathematics was not merely difficult, it was logically impossible. And Gödel proved this with a proof. The philosophical implications are staggering. Mathematics is not a closed system where every truth can be captured by a fixed set of rules. It is open-ended, inexhaustible. There will always be more to discover, and there will always be truths that lie just beyond the reach of any particular framework. And the story does not end with Gödel. Because his work inspired another mathematician, a young Englishman named Alan Turing, to think about a related question. Gödel had shown that certain statements are unprovable. Turing asked a complementary question. Are there problems that are unsolvable, not by any particular method, but by any method at all? Is there a limit to what computation can do? In 1936, Turing published a paper that defined, with mathematical precision, what it means to compute something. He imagined an abstract machine, absurdly simple in its design, just a tape divided into cells and a read-write head that moves along the tape following rules. This machine, now called a Turing machine, can be instructed to perform any computation that any real computer can perform. It is the theoretical foundation of computer science, and Turing proved that there are problems that no Turing machine, and therefore no computer of any kind, can solve. The most famous is the halting problem. Given a description of a program and its input, decide whether the program will eventually stop or run forever. Turing proved that no general algorithm can solve this problem. The unsolvability is not practical, but fundamental. There is no amount of cleverness or computational power that will ever overcome it. Turing's work, alongside that of Alonzo Church, who reached similar conclusions by different methods, defined the very boundaries of what algorithms can and cannot do. And within a decade, actual physical computers were being built, and the abstract theory of computation became the foundation of the most transformative technology in human history. Let me also tell you about Emmy Noether, because her story speaks directly to the question of mathematical structure and the power of asking why. Amalie Emmy Noether was born in 1882 in Erlangen, Germany. Her father was a mathematics professor, and she showed mathematical talent from an early age. But this was Germany in the late 19th century, and women were not allowed to enroll as regular students at the university. Noether attended lectures as an auditor, meaning she could sit in but received no credit and could not take exams. She eventually earned her doctorate in 1907, but finding a position was nearly impossible. Even after she moved to Göttingen, then the most important center of mathematics in the world, she could not hold an official faculty position. David Hilbert, who recognized her brilliance, tried to get her appointed. The faculty objected. "What will our soldiers think when they return to the university and find they are expected to learn at the feet of a woman?" one colleague argued. Hilbert reportedly replied, "I do not see that the sex of the candidate is an argument against her admission. After all, we are a university, not a bathhouse." Despite these obstacles, Noether did some of the most important mathematical work of the 20th century. Her most famous result, Noether's theorem, published in 1918, establishes a deep connection between symmetry and conservation laws in physics. Every symmetry of a physical system corresponds to a conserved quantity. The fact that the laws of physics are the same today as they were yesterday, symmetry under time translation, gives you conservation of energy. The fact that the laws of physics are the same here as they are 10 feet to the left, symmetry under spatial translation, gives you conservation of momentum. The fact that the laws look the same regardless of which direction you face, rotational symmetry, gives you conservation of angular momentum. This is one of the deepest results in all of mathematical physics. It connects the abstract notion of symmetry, which belongs to group theory, Galois' creation, to the concrete conservation laws that govern the physical world.
Einstein called Noether the most significant creative mathematical genius thus far produced since the higher education of women began. Noether was Jewish, and when the Nazis came to power in 1933, she was dismissed from her position. She emigrated to the United States and took a position at Bryn Mawr College. She died in 1935 at the age of 53 from complications following surgery. She had been one of the greatest algebraists of the 20th century, and her work on abstract algebra, on rings and ideals, and the structural foundations of the subject reshaped the field completely. Before Noether, algebra was largely about solving equations. After Noether, algebra was about understanding abstract structures and the relationships between them. She asked why things worked, and her answers changed what mathematics looks like. Now let me tell you about one more person, because his story captures something essential about the nature of mathematical discovery. His name was Srinivasa Ramanujan. Ramanujan was born in 1887 in Erode, a small town in southern India. He grew up in poverty, largely self-taught in mathematics, working from a single, outdated textbook. He had almost no formal training beyond high school, and yet, working alone in Madras, with no access to the mathematical literature and no colleagues to talk to, he produced results of such stunning originality and depth that when they eventually reached the attention of professional mathematicians, they were astonished. In 1913, Ramanujan wrote a letter to G.H. Hardy, a mathematician at Cambridge University in England. The letter was 10 pages long and contained a long list of mathematical formulas, stated without proof. Hardy's first reaction was that the letter was probably the work of a crank.
He almost threw it away. But something made him look more closely. And as he and his colleague, J.E. Littlewood, began to work through the formulas, they realized they were looking at something extraordinary. Some of the formulas were known results, which Ramanujan had rediscovered independently. Some were new, and when Hardy and Littlewood tried to prove them, they succeeded, confirming that Ramanujan was right. And some were so strange, so unexpected, that Hardy could not figure out where they came from. He later said that these formulas defeated me completely. I had never seen anything in the least like them before. A single look at them is enough to show that they could only be written down by a mathematician of the highest class. Hardy arranged for Ramanujan to come to Cambridge, and for the next 5 years, the two of them collaborated in one of the most remarkable partnerships in the history of mathematics. Hardy provided the rigorous training that Ramanujan lacked. Ramanujan provided an intuition and a creative power that Hardy found almost supernatural. Hardy later rated mathematical ability on a scale from 0 to 100. He gave himself a 25, he gave Littlewood a 30, he gave Hilbert an 80, and he gave Ramanujan 100. Ramanujan's health, never strong, deteriorated in the cold, damp English climate. He was a strict vegetarian and a devout Hindu, and he struggled to find suitable food during wartime rationing. He contracted tuberculosis and returned to India in 1919. He died in 1920, at the age of 32, leaving behind notebooks filled with thousands of results, many of them unproved, many of them not understood until decades later. What makes Ramanujan's story so remarkable for our purposes is the sheer mystery of where his insights came from. He had almost no exposure to modern mathematics. He worked in isolation, and yet he produced results that anticipated developments that would take the rest of the mathematical world decades to reach.
He seemed to see mathematical truths directly, without the intermediate steps of proof and derivation that other mathematicians relied on. When asked how he came up with his formulas, he reportedly said that the goddess Namagiri revealed them to him in dreams. Hardy, a committed atheist, found this explanation unsatisfying, but he could not offer a better one. Ramanujan's work remains one of the great mysteries of mathematical creativity, a reminder that the question of why, the question of what makes mathematics true, and how human beings discover those truths, is not fully answered. Let me also expand on the question of proof itself, because the concept is so central and so often misunderstood. Mathematical proof is not like scientific evidence. Scientific evidence is always provisional.
No matter how many experiments confirm a theory, a single counterexample can overturn it. Newton's theory of gravity was confirmed by 200 years of observations before Einstein showed it was incomplete. Science proceeds by accumulating evidence and building theories that are always subject to revision. Mathematical proof works differently. A proof is a logical argument, starting from accepted axioms, proceeding through a chain of deductive steps, each one following necessarily from the previous ones, arriving at a conclusion that must be true if the axioms are true. There is no wiggle room, no margin of error, no possibility of future revision. Once a theorem is proved, it stays proved forever. This gives mathematics a kind of permanence that no other human endeavor possesses. The theorems Euclid proved in 300 BC are just as true today as they were then. They will be true in 1,000,000 years. They were true before Euclid proved them.
The proof did not create the truth. It revealed it. And the concept of proof has been refined and extended in remarkable ways over the centuries. In the 20th century, computers entered the picture. In 1976, Kenneth Appel and Wolfgang Haken proved the four-color theorem, which states that any map can be colored with at most 4 colors such that no 2 adjacent regions share the same color. Their proof relied on checking thousands of individual cases by computer. It was the first major theorem whose proof required computer assistance, and it generated intense debate. Many mathematicians felt uneasy. A proof you cannot check by hand, a proof that depends on trusting that a computer program has no bugs, is that really a proof? The debate has not been fully resolved, but computer-assisted proofs have become increasingly common and increasingly accepted. More recently, proof assistants, software programs that can verify the logical correctness of mathematical arguments, have begun to change the way some mathematicians work. Systems like Lean and Isabelle allow you to formalize a proof in a computer-checkable language. Every step must be justified, every assumption must be explicit, and the computer will not accept an argument that contains a gap or an error. Some mathematicians are now formalizing large bodies of mathematics in these systems, creating a verified mathematical library that is guaranteed to be correct. This connects back to Hilbert's dream in a way he could not have anticipated. Hilbert wanted a formal system that could capture all of mathematics and be verified for consistency. Gödel showed that no single system could do this. But computer-verified proofs offer something different, not a universal foundation, but a practical tool for ensuring that specific proofs are correct, one theorem at a time.
The dream of absolute certainty is dead, but the pursuit of verified correctness is very much alive. And alongside the formal tools, there is the question of mathematical beauty, which is harder to define, but deeply felt by every working mathematician. G.H. Hardy wrote in his memoir, A Mathematician's Apology, that beauty is the first test. There is no permanent place in the world for ugly mathematics. Paul Erdős spoke of proofs that came from the book,
an imaginary book in which God keeps the most elegant proof of every theorem. When a proof is particularly beautiful, Erdős would say, "That's from the book." What makes a proof beautiful? Clarity, economy, surprise? A beautiful proof illuminates why something is true, not just that it is true. It reveals a connection you did not see before. It makes you feel that the result could not have been otherwise, that the truth was hiding in plain sight, and the proof simply drew back a curtain.
And speaking of beautiful proofs, let me finally tell you the story I promised earlier. The story of the recluse who refused $1 million. Remember the Poincaré conjecture, the great open problem in topology that we mentioned when we were talking about shapes? It had been open for nearly 100 years. Dozens of mathematicians had tried to prove it and failed. Some had published proofs that turned out to contain errors. It was one of the 7 Millennium Prize problems, carrying a $1 million reward. In 2002 and 2003, a Russian mathematician named Grigory Perelman posted a series of papers on the internet. Not in a peer-reviewed journal, on the internet, on a preprint server called Archive. The papers were dense, technical, and contained almost no motivation or background. They simply presented the argument, and the argument proved the Poincaré conjecture.
Perelman's proof used techniques from differential geometry and a process called Ricci flow, which smoothly deforms a shape the way heat smooths out temperature differences in a metal bar. The curvature flows and evens out, gradually revealing the underlying topological structure. It was a brilliant synthesis of geometry, analysis, and topology, drawing together ideas from all three of our earlier questions: shape, change, and certainty, into a single argument. The mathematical community spent several years checking the proof. It held up. Perelman was awarded the Fields Medal, the highest honor in mathematics, in 2006. He declined it. In 2010, the Clay Mathematics Institute awarded him the Millennium Prize of $1 million. He declined that, too. He reportedly said that he was not interested in money or fame, and that the mathematical community's recognition was not something he valued.
He has lived in seclusion in St. Petersburg ever since, and he has published no further mathematics. The contrast with Galois could not be sharper. Galois, desperate to be heard, submitting papers that were lost and rejected, scribbling his ideas in the margins the night before his death. Perelman offered the highest honors the mathematical world can bestow, turning them down and walking away. Two completely different relationships to mathematical recognition, bookending the modern history of the question, why? Now, let me bring this story forward to the present, because the question of why, the question of proof and certainty and the limits of knowledge, is very much alive today. Remember the Riemann hypothesis from the first chapter? In 1859, Bernhard Riemann, the same mathematician who gave us the geometry that Einstein would later need, wrote an 8-page paper about prime numbers. In it, he studied a special function called the zeta function, and noticed that its non-trivial zeros all seem to fall on a specific vertical line in the complex plane, the line where the real part is exactly 1/2. He noted this almost casually, as an observation rather than a formal claim. That observation became the Riemann hypothesis, and it is now the most important unsolved problem in pure mathematics. If it is true, it would mean that the prime numbers are distributed as regularly as they possibly could be, given their overall density. The primes would have a kind of deep orderliness underneath their apparent randomness. If it is false, if even 1 zero lies off the critical line, our entire picture of the primes would need fundamental revision. Computers have checked the first 10 trillion non-trivial zeros. Every single one sits exactly on the half line. But 10 trillion is not a proof.
In mathematics, there are examples of things that appear true for billions of cases and then turn out to be false. We need a proof that covers every zero, every one of the infinitely many non-trivial zeros, all at once. The Goldbach conjecture, proposed in a letter from Christian Goldbach to Leonhard Euler in 1742, states that every even number greater than 2 is the sum of 2 primes. 4 equals 2 plus 2. 6 equals 3 plus 3. 8 equals 3 plus 5. 28 equals 5 plus 23. Every even number that has ever been checked, up to 4 quintillion, breaks into 2 primes. Nobody can prove it must always be true. The Collatz conjecture is even simpler to state. Pick any positive whole number. If it is even, divide it by 2. If it is odd, multiply by 3 and add 1. Repeat. The conjecture says you will always eventually reach 1. 27, for example, takes 111 steps, bouncing up to a peak of 9,232 before spiraling back down to 1. Every starting number anyone has ever tried, up to about 295 quadrillion, eventually reaches 1. Nobody has proved it. Paul Erdős, one of the most prolific mathematicians of the 20th century, said that mathematics is not yet ready for such problems. And then there is P versus NP, perhaps the most practically important unsolved problem in mathematics. It asks whether every problem whose solution can be quickly verified can also be quickly found. If you can check a proposed solution to a Sudoku puzzle in a few seconds, does that mean there is a fast algorithm for solving Sudoku puzzles in general? We do not know. If P equals NP, it would mean that enormous classes of problems we currently consider intractable are actually solvable by fast algorithms we have not discovered yet.
It would revolutionize computer science, cryptography, logistics, and dozens of other fields. If P does not equal NP, as most experts suspect, it would mean that there are fundamental limits to what efficient computation can achieve. Either way, the answer would be one of the most consequential results in the history of human knowledge. The Clay Mathematics Institute has offered $1 million for the proof. These problems are not obscure puzzles for specialists. They sit at the heart of what mathematics is and what it can do. They connect to physics, to computer science, to the structure of the natural world, and they remain stubbornly, gloriously open. So where does all of this leave us? We started with 4 questions. How many? What shape? What if it changes? Why must it be so? And what I hope you can see now is that these questions are not 4 separate stories. They are one story, told from 4 different angles. And the angles keep meeting and merging and splitting apart and meeting again. The question of how many leads to numbers, and numbers lead to algebra, and algebra leads to the question of whether equations can be solved, which leads to group theory, which leads to symmetry, which leads to the deepest structures of physics. The question of what shape leads to geometry, and geometry leads to coordinates, which merge geometry with algebra, and the merger leads to calculus, which answers the question of what happens when things change. And all of these, every single one, depend on the question of why, on the concept of proof, on the demand for certainty that the Greeks introduced, and that Gödel showed has fundamental limits. Mathematics is not a collection of separate subjects. It is one enormous interconnected web of ideas, and pulling on any thread eventually leads you to every other thread. The algebra of Al-Khwarizmi connects to the geometry of Euclid, connects to the calculus of Newton, connects to the groups of Galois, connects to the sets of Cantor, connects to the logic of Gödel, connects to the computation of Turing. One continuous thread stretching from scratches on a bone to the most powerful technology humanity has ever built. And the thread is not finished. Right now, tonight, mathematicians are working on problems that connect these old questions in new ways. The Langlands program, initiated by Robert Langlands in the 1960s, proposes deep connections between number theory and geometry that would unify vast areas of mathematics in ways we are only beginning to understand. Topological data analysis uses the mathematics of shape to find patterns in high-dimensional data. Quantum computing is forcing mathematicians to rethink the foundations of complexity theory. New areas keep emerging. New connections keep being discovered.
The frontier is as wild and open as it has ever been. And maybe the most remarkable thing about the whole story is this: mathematics works. The abstract structures that human beings invented, or discovered, depending on your philosophical inclination, structures developed for reasons of pure curiosity and aesthetic pleasure, keep turning out to describe the physical universe with breathtaking precision. Nobody fully understands why. The universe, for some reason, is mathematical. The patterns are real. The structures are out there, encoded in the fabric of reality, waiting for someone to notice them. Somewhere right now, somebody is noticing one. Maybe in a university office with a whiteboard covered in symbols. Maybe at a kitchen table with a notebook and a pencil. Maybe in the mind of a student who does not yet know that the thing they are puzzling over connects to something that has been open for 160 years. The questions are still alive.
They have been patient for a very long time. They do not mind waiting a little longer. The Ishango bone is roughly 20,000 years old. The clay tablets of Babylon are about 4,000 years old. Euclid's Elements is 2,300 years old. Newton's Principia is 340 years old. Gödel's incompleteness theorems are less than 100 years old. The arc of the story keeps bending forward, keeps accelerating, keeps opening up new territory faster than anyone can map it. And the beautiful thing, the truly astonishing thing, is that you are part of it. Not as a spectator, but as a participant. Every time you count change, you are using a place value system invented in India and carried to Europe by Arabic scholars. Every time you check a map on your phone, you are relying on the curved geometry of Riemann and the satellite technology that depends on Einstein's corrections to Newtonian physics. Every time you send an encrypted message, you are protected by the properties of prime numbers that Euclid proved are infinite and that Riemann's hypothesis seeks to understand. Every time you watch a weather forecast, you are seeing the output of differential equations that Newton's calculus made possible and that chaos theory showed have fundamental limits. Mathematics is not something that happens in textbooks and classrooms. It is the invisible architecture of your daily life. It holds up the buildings you live in, moves the information you consume, secures the transactions you make, predicts the weather you dress for, and shapes the technology you carry in your pocket. 20,000 years of asking how many, what shape, what if it changes, and why must it be so, and the answers are woven into everything around you. So let that thought settle. Let the numbers and the names and the stories find their places, like stones fitting into a mosaic.
Somewhere tonight, on a quiet desk in some corner of the world, a sheet of paper is filling up with symbols. Someone is thinking. Someone is reaching. Someone is asking one of those 4 old questions in a new way. And maybe, just maybe, they are about to find something that nobody has found before. The story is not over. It has never been over. And that might be the most remarkable thing about mathematics. It is the oldest continuous intellectual project in human history. And it is still, after all these thousands of years, just getting started. 20,000 years ago, someone carved notches on a bone. Tonight, someone is proving a theorem. Tomorrow, someone will ask a question nobody has thought to ask yet. The thread is unbroken. The questions are still alive.
And somewhere in the quiet, in the space between what we know and what we do not, the next answer is already taking shape, patient and luminous, waiting to be seen. Let that be enough for tonight. The mathematics will still be there in the morning. All of it. Everything we talked about and everything we did not get to.